Good morning, everyone. We are going to get started. It is 8:58. Today we'll be going over the updates to Chapter 5 through 13 of the Field Sampling Procedures Manual. Next slide, please. Okay, my name is Kyle Kubler. I will be co-moderating today's training with Taylor Dobson. Both of us are part of the Contaminated Site Remediation and Redevelopment Training Committee. Next slide, please. Today's training has been approved for 3.5 technical continuing education credits. There is an attendance requirement that must be met in order to receive the credits. In order to receive the continuing education credits, participants must be logged in for the entire session and answer 3 out of 4 poll questions, which will be randomly inserted throughout the presentation. If any issues arise while answering the poll questions, please notify us immediately via the chat or questions function. Thank you. Next slide, please. So what's the process for getting continuing education credits? Once this training is over, the DEP will provide the LSRPA a list of eligible participants for the continuing education credits. The LSRPA will then reach out to you individually with instructions on how to access the certificates. Certificates will be issued by the LSRP after paying a $25 processing fee. Next slide, please. This is going to be an example of test your knowledge. Next slide, please. As previously mentioned, test polls are randomly inserted throughout today's training. Again, this is just an example. No participation is required. When a test poll question does come up, there should be a pop-up screen that appears. From there, you may submit your answer. It does not matter if you answer the questions right or wrong. You just have to answer the questions. Next slide, please. This is how you communicate with us in GoToWebinar. Within GoToWebinar's toolbar, there is a questions function. Please ask any questions you have for presenters at any time during the presentation. These will be addressed during the questions segment. If a question is not addressed during a question segment of the presentation, it will be answered after the presentation. Questions should be brief and general. Also, please refrain from case-specific questions. Thank you. Next slide, please. Please don't forget to fill out a course evaluation. The course evaluation can be accessed using the URL below and also will be entered into the chat. Next slide, please. Your job for this training is to participate by asking questions, completing the polls, in addition to providing feedback for the course evaluation. Next slide. Thank you very much. Next up, we have Julia Ryan from the LSRPA.
Hello, everyone. Welcome to this training. The LSRPA, as we all know, is our association for licensed site remediation professionals. We have a lot of education and other events, and we're going to go through some of that now. Next slide, please. So we can't have an association really without our partners, so we want to thank our diamond partners. Next slide. Our gold partners. And next slide, our silver partners. Next slide, please. We have some excellent upcoming courses and events. On March 5th, we're going to have Women in Environmental, Construction, Architecture, and Engineering Professions. That'll be put on with Sue Boyle, Shanine Mitchell from the US EPA, and Mimi Ray Gorodetsky at Langen. Hopefully I didn't bungle that. March 12th, 2024, we're going to have a regulatory roundtable on unmanned aerial systems. So basically, how can you use drones to better assess your sites? March 19th, 2024, we're going to have a remediation funding source and financial assurance training with Jennifer McLeod and Vincent Fasanella at the DEP, as well as Christopher Venezia and LSRP at ESA Environmental. Next slide, please. We have an Aspiring Professionals course coming up on March 27th, the Life of a Project and Project Management presentation. So get your aspiring professionals into that. It should be a very good course. And then on April 16th and the 18th, we have an 8-hour HAZWOPER refresher being put on by David Sweeney. Next slide, please. We are 34 days away from the annual conference. So if you have not registered yet, if you have not gotten your hotel yet, please do. We have an excellent slate of 12 courses, including topics like artificial intelligence. Should be a very good education time and a great networking event. Next slide, please. And Battle of the Bands, very popular, coming up on May 9th. Get your tickets, get out there. It's always a fun time. Very much recommended. Next slide, please. And of course, how can you interact with the LSRPA? We're on LinkedIn, we're on X, and we're on Facebook. Next slide, please. And if you're not a member, please join. There are a lot of great events and access to different member-only services. It's really worth the membership fee. So join today. Next slide, please. All right, thank you to everyone and have a great course.
Thank you, Julia. Up next, we have Crystal Perisic doing the introduction.
Thank you, Julia. Good morning, everybody. My name is Crystal Perisic. I work for the New Jersey Department of Environmental Protection in the Bureau of Site Management. I am also the chair of the Field Sampling Procedures Manual Committee. Next slide. Our committee is made up of 31 individuals. This is a list of our DEP members. Next slide. And our stakeholder members. Next slide. A little bit about the history of the manual. The original document was put out for use in 1992. This was, of course, a paper copy only. It was created to promote accuracy and consistency, and it discussed how environmental samples are collected and analyzed. Next slide. There was a complete rewrite of the manual in 2005, and this was our first electronic copy. Next slide. Since 2005, there were a few minor updates for text and clarification, the last of which was in 2011. Below is a link to the list of all of the updates that have been done. Next slide. And that brings us to our current version. We started the committee in fall of 2017, and we were tasked with updating every chapter of the manual. Next slide. Along the way, we have also been updating the website. As you can see, on the right-hand side, there is a link to the past version of the manual. Down the center is all of the chapters. And then on the left-hand side, we added a training tab that will go right to the training website to these specific trainings. We also did an acronyms and a glossary tab for ease of use. Next slide. Again, the glossary and acronyms are new to the website. Next slide. So how did the process work? Since we have 31 members in our committee, we divided up into work groups for each chapter. Each work group was tasked with updating and revising the chapter. When the work group was complete, it was then given to the entire committee for review and comment. Once the entire committee was done with their review and comment and everything was updated, it then went out for NJDEP review and stakeholder review. All comments were reviewed and discussed within the work group as well as the entire committee. Next slide. CSRR does allow for deviations from all technical guidance, including Field Sampling Procedures Manual. So if you choose to deviate from this guidance, you should document in each of your reports that your method is equally protective and document any special site-specific circumstances. Next slide. And the use of equipment names in this manual is just for informational purposes and does not constitute an endorsement. The sampling technologies are provided as examples and are not all-inclusive. Next slide. This is a list of all of the chapters within the manual. As you can see, it goes up to chapter 13. The previous manual had chapter 14, but chapter 14 and 13 were combined. Next slide. Chapters 1, 2, and 4 were posted for use and trained in March of 2022. That training can be found under the training tab on the website. Next slide. Chapter 3 was replaced with contaminants of emerging concern. This chapter has gone out for external review. The work group is finishing comments that were received and will hopefully be posted for use in the next few weeks. Next slide. The first work group that we're going to talk about today is chapters 5 and 6. This is a list of all of the members of that work group. That was posted for use in November of 2022. Next slide.
Okay, thank you, Crystal. Up next, we have Catherine Janjacek and Greg Giles to discuss the updates to Chapter 5, Sampling Equipment.
Good morning. My name is Catherine Janjacek, and I am part of the DEP at the New Jersey Geological and Water Survey. Next slide. Chapter 5 covers equipment for field sampling. This slide provides an overview of the chapter. Chapter 6 will go into sampling methods. This chapter has a lot of content, so I'll be focusing primarily on updates from the previous version of the manual and some key points. Next slide. The introduction of the chapter starts with construction material, sampling equipment, and supplies. The topic of tubing specifically will be discussed in Chapter 6. The considerations when selecting sampling equipment are listed here and includes the type of sample, the sample matrix, where the sampling point is located, and other site conditions. In addition, sample and construction material compatibility should be considered, and more information is provided in Table 5.1 in this chapter about materials of construction. The table provides a description of construction materials, including plastics, metals, and glass, and lists compatibility with target analytes. Section 5.1.2 mentions specifically that it is not recommended to use fluoropolymers such as Teflon with PFAS sampling. Next slide. This topic is further continued to discuss avoidance of negative bias, which is bias that would underestimate analyte concentrations. This is especially important when sampling for VOCs and other compounds that tend to absorb, like PFAS. A sampling material's absorption-desorption capacity becomes more important the lower the contaminant concentration and the lower the groundwater quality standard. At low levels, the effect of adsorption or desorption could change the interpretation of the data. This issue should be discussed in documents where high-density polyethylene versus low-density polyethylene is used and the sampling data are presented. Low-density polyethylene tends to have higher absorption than a higher-density polyethylene. Next slide. As the manual does not include every possible type of sampling device, documentation should be submitted on sampling devices and sample collection methods that are not included. Examples of the information that should be included are listed here on this slide. Inappropriate application of a sampling device or failure to provide adequate supporting documentation can result in rejection or downgrade, such as lowering of data to screening quality of the data by DEP. Next slide. Chapter 5.2 now includes decontamination. This section was moved from Chapter 2 and edited for clarity. In addition, the disposal of IDW is now in Chapter 5. That was also previously in Chapter 2. IDW disposal will be discussed by Greg Giles in the next few slides. For decontamination procedures, in most instances, fixed laboratory decontamination is preferred to field decontamination, but options exist for field decontamination for everything except balers. Decontamination is an important aspect of quality control. Improperly cleaned and prepared sampling equipment can lead to misinterpretation of environmental data due to interference caused by cross-contamination. The decontamination procedures are the same as the previous version of the manual, but some of the name of the decontamination procedure using heat was changed from a longer title starting with U.S. Army cold regions. So the 8-step decontamination procedure for aqueous and non-aqueous sampling equipment, the main change there was that ASTM type 1 deionized water was added in addition to type 2 as being suitable. The 8 steps very briefly are detergent, tap water, DI water, acid if sampling for metals, DI water, solvents for trace organics, air dryer nitrogen, and DI water. The 3-step decontamination procedure is for non-aqueous sampling equipment only, and that's basically a detergent scrub, water, DI water, and then a solvent if applicable. The decontamination procedures using heat, an example of that would be for use with direct push equipment using steam cleaning or hot pressure wash. The last type of decontamination procedure is the USGS decontamination procedure for low-level contamination. This is less used for sampling of contaminated sites. It's more for trace levels. The details were removed and it's just linked directly to USGS, as these are USGS procedures. This section goes on to go over general decontamination considerations and specifics to pumps and other specific cases such as heavy equipment, direct push equipment are listed there. And now Greg Giles will take over to discuss the disposal of investigation-derived waste.
Thank you. Good morning, my name is Greg Giles. I'm a geologist with the Bureau of Groundwater Pollution Abatement, and I will be briefly discussing investigation-derived waste, or IDW. Investigation-derived waste is soil, water, and personal protective equipment that is generated during remedial activities. Language outlining how to store and dispose of the generated waste should be addressed in the related sampling plan. Discussions on investigation-derived waste can now be found in 3 sections of the manual. The locations of the IDW discussions are shown on the slide. Next slide, please. Personal protective equipment includes items such as disposable gloves, booties, Tyvek, and contaminated equipment. Soil IDW includes soil generated from soil borings, soil sampling, well installation, and decontamination of people and equipment. Water IDW includes water generated from well installation, well development, well sampling, and decontamination activities. IDW-related changes in the manual were limited to the disposal options for groundwater generated during well sampling, so my talk will only cover that issue. Next slide, please. General options for the disposal of water generated from well sampling include discharging the water to ground at the well location. Where the well location is not amenable to a discharge to ground, you can transport the water to an on-site location and discharge the water where like soil contamination has been documented or where first water is contaminated with like contaminants. You may be able to discharge water to a local stormwater or sanitary sewer system. While not specified in the Field Sampling Procedures Manual, it is important to note that this option would require water quality documentation and approval from the respective municipality or utility. Next slide, please. When planning your disposal options for the generated water, it is important that you are familiar with the language in the New Jersey Administrative Code 7:14A, Section 7.5. This statute allows for water generated from well installation, well development, and well sampling to be discharged to ground via a permit by rule. There is no volume limit and no written approval from DEP is required. Next slide, please. When considering the discharge to ground option, the discharge to ground should not result in a discharge of water-containing product, a discharge of contaminated water from a lower aquifer to a non-impacted water table aquifer without treatment, a discharge of contaminated water to clean soils at concentrations that would result in the development of contaminated soil unless the water is treated first. Next slide, please. Where it is determined that generated water is contaminated at concentrations that would preclude a direct discharge to ground, the use of a portable treatment system may allow the groundwater quality to be improved to the point where the water can be discharged to ground. Examples of field treatment for VOCs would include such options as bubble aeration, tray aeration air stripping, or activated carbon. This concludes my discussion on IDW. Thank you.
Section 5.3 covers aqueous and other liquid sampling equipment. This slide provides an overview of Section 5.3. Most of the changes were made in Section 5.3.1, groundwater sampling equipment. Overlap may occur between sections as some equipment may have multiple applications. When in doubt, all sections should be consulted. Next slide. The submission of well purging information was added to this chapter for emphasis. Well purging information should be recorded and submitted to DEP on a sampling log, form, or table, including depth of water, amount of well drawdown induced during well purging, the well intake interval, and sometimes groundwater chemistry, also known as water quality indicator parameters, collected by a company that has laboratory certification. This will be discussed further in Chapter 6. Assessing the drawdown in the well intake interval is critical to evaluate the potential loss of pressure-sensitive compounds. Additionally, comparing the well purge rate to well drawdown data may allude to the well recharge capacity. Changes in the water quality parameters during purging show the difference in water quality within the well and the surrounding formation. The changes in water quality parameters should be evaluated when considering implementing a no-purge sampling method. Well purging information and well purge logs will be further discussed in Chapter 6 and Chapter 9. Next slide. Section 5.3.1 is groundwater sampling equipment, and it begins with purge sampling equipment, which basically is pumps and bailers. Again, brands listed here are for descriptive purposes and are not an endorsement and don't cover all possible types of pumps. This section was reorganized into negative and positive pressure pumping equipment. Negative pressure pumping equipment withdraws air to move fluids through tubing by development of a vacuum, similar to drinking from a straw. These include suction lift pumps such as diaphragm, surface centrifugal, and peristaltic pumps. To prevent water from draining into a well when using these types of pumps, either keep the pump on or use a check valve at the bottom of the tubing. With negative pressure, accurate and reproducible measurements of volatile compounds, organic and inorganic, and air-sensitive parameters cannot be obtained. This bias is extended to samples collected for, but not limited to, volatile organics, dissolved oxygen, pH, carbon dioxide, and iron. As a result, these types of devices are not recommended for the collection of samples for volatile organic compounds and higher vapor pressure semi-volatile organic compounds and M&A parameters. Positive pressure pumping equipment uses positive pressure, which refers to the development of pressures greater than the relative atmospheric pressure. This equipment develops an internal spot of high pressure through the inflation of a bladder, turning of a gear, or rotation of an impeller that forces groundwater up a section of tubing. The different types of pumps are listed here, and they have not changed from the previous version of the manual. Also in this section, packers are listed, which are an accessory deployed in conjunction with pumps for specific circumstances, and also bailers, bottom fill bailer and double check valve bailer. Of note, samples taken from bailers may not represent the specific depth interval to which the bailer is lowered. Water entering the bailer doesn't necessarily enter the bailer at a rate at which it is lowered. Bailers must be lab cleaned or disposable. Next slide. The next section is no purge or passive sampling. This slide defines no-purge sampling as a sampling technique using a device specifically designed to obtain a sample of limited volume within the well intake interval without well purging prior to sample collection. It acquires a sample from a discrete location without inducing active media transport, and it relies on being exposed to media and ambient equilibrium during a sampler deployment period. The term no-purge is used because certain sampling devices technically are considered active because you are grabbing a sample. I'll go into that in the future. So no-purge samplers can be divided into two general categories, passive and active samplers. They can be further subdivided into three categories, diffusion samplers, passive grab samplers, and accumulation samplers. An example of a no-purge active grab sampler is the hydrosleeve sampler. Vertical profiling with passive samplers will be discussed in Chapter 6, as well as technical limitations. Some passive samplers cannot be used for all analytes. Passive samplers may not be able to collect sufficient sample volume for all required analyses. Some passive samplers may not fit into wells. Some devices are not appropriate for total or unfiltered sample analysis because of diffusive filtration, and some methods, the absorptive methods, produce a calculated concentration rather than a measured concentration. Next slide. Each section within the groundwater sampling equipment in the manual discusses applications, limitations, and use. On this slide, the technologies that were added to the new version of the manual are circled. And again, this is not an all-inclusive list. So the new additions are the hydrosleeve, the SNAP sampler, nylon screen passive diffusion sampler, regenerated cellulose dialysis membrane sampler, dual membrane passive diffusion bag sampler, rigid porous polyethylene sampler, peeper sampler, and the AGI universal sampler. A passive diffusion bag sampler is shown in this figure. They were described in detail in the previous version of the manual. Next slide. So one subtype of no-purge sampling equipment are grab sampling technologies, including the hydrosleeve, SNAP sampler, and syringe sampler. So grab sampling technologies are basically when a whole water sample is collected as opposed to diffusion-based methods, which are filled with DI water and deployed in a well, and then based on diffusion. These are whole water samples. So the 3 examples are here. I'll focus on the SNAP sampler and HydroSleeve because the syringe sampler was in the previous version of the manual and is not as commonly used. So a SNAP sampler has a module as shown in this figure that contains a bottle with caps on both ends that are left open, and then when the sample is collected, it's spring-loaded and the caps close, and the whole apparatus can be pulled out of a well, and then those bottles can be either submitted to a laboratory if the laboratory can handle them, or they can be decanted into a sample bottle, and then the plastic modules can be reused. They have to be dedicated to an individual well. One of the advantages, it is a fixed system, so samples will always be collected at the same depth because that whole assembly will go back down to the same depth as before. They do have a 2-week deployment period that is recommended. A HydroSleeve is shown in the center figure, and it is basically a thin polyethylene sleeve that is deployed into a well on a tether, and it has to be deployed below the selected portion of the screen interval that the sample will be collected from, and then to fill the HydroSleeve, the user has to pull it up. Next slide. Due to the relative complexity of HydroSleeve deployment and the sampling technique, we included this figure to kind of illustrate. There is room for user error with HydroSleeves. The minimum deployment period recommended is 48 hours, though there are circumstances where a longer deployment period may be necessary due to aquifer conditions. The equilibration period is to allow for the well to return to its initial condition and also for the HydroSleeve material to equilibrate chemically with the water conditions. The HydroSleeve can sample for any parameter if volume allows, and a new HydroSleeve can be installed when one is retrieved. So to deploy the HydroSleeve, it is lowered into the well with a weight at the bottom, and it is either deployed, it can either have a bottom weight or a top weight depending on the size of the well. It might need to be compressed down at the bottom of the well if you need to sample at the very bottom. And then it should be pulled up quickly to fill after its equilibration period at approximately a rate of 1 foot per second. And then at the top is a reed valve, and it closes automatically when the HydroSleeve is full. That's where user error can come in. Sometimes if the bag does not fill, the bag would need to be redeployed and allowed to re-equilibrate. Next slide. So the next type of no purge sampling equipment are the diffusion sampling technologies. So as I mentioned before, the passive diffusion bag sampler, or PDB, was described in great detail in the previous version of the manual. So the circle technologies are the ones that were added. A number of these are not they're not as commonly used or possibly not as widely commercially available. So I'm going to focus on only a few of them and then show some illustrations of the other ones. So the limitations of diffusion sampling technologies as a whole is that not all compounds can be sampled by each type of diffusion sampler. Generally, diffusion samplers should not be used at a site until contaminants of concern have been thoroughly documented and are determined to be compatible. Membrane limitations restrict accurate pH, specific conductance, or temperature data. One change from the previous version of the manual is that it now states that diffusion samplers can be filled with either ASTM type 1 or type 2 water, and they must be submerged during the full deployment time in the well intake interval. So if the well has fluctuations in the water table, that has to be accounted for. This picture shows a dual membrane diffusion bag sampler, or a dual membrane PDB. So it's similar to a standard PDB, except as you can see in the picture, it's important that the nozzle and the plug is oriented upward on the cap up, because the upper membrane is coarser. It allows large or polar molecules to pass through. So it has to be oriented upward. It has like a rigid internal frame, and it must be deployed for a minimum of 21 days, unlike the standard PDB. But they're similar in the deployment to a standard PDB with a tether and a weight. And it's somewhat similar in appearance, though, with the rigid internal frame and then the coarser mesh at the top. Next slide. So these are just diagrams showing some of the other sampler types. So the nylon screen passive diffusion sampler is basically a bottle with a mesh nylon screen over a cap with an opening, and they can be deployed in series. And then the regenerated cellulose dialysis membrane sampler, it's a membrane filled with deionized water, but it has a limitation of it is subject to the degradation. It can't be left in a well as long as like a polyethylene product would be, and they're relatively fragile. Next slide, please. And then there's the rigid porous polyethylene sampler, and those are also less widely used, and then the peeper sampler. So peeper samplers are largely used to study pore waters from groundwater or surface water interfaces such as streams, rivers, wetlands, etc. Peeper samplers are capable of monitoring most inorganic and organic compounds present in dissolved phases, and there are different types of peeper samplers. Next slide, please. The third category of no-purge sampling are accumulation or absorption sampling technologies. The example listed is the AGI universal sampler, formerly known as the Goresorber, and that's depicted here. That will be discussed further in Chapter 9, discussing soil gas. There are other types of accumulation or absorption passive sampling technologies, including POSIS, but basically of note is they're all considered screening level data only, and samples are a time-integrated representation of conditions at the sampling point over the entire deployment period. And next slide, please. Also discussed in this section is the direct push technologies for groundwater sampling. It just discusses general considerations when using direct push for groundwater sampling. An example of an application would be to obtain vertical profile information because multiple discrete samples can be collected from the same borehole, and that can help determine where to set a permanent well screen before doing so. So basically, equipment should be properly decontaminated using heat between each use, and then sample collection tubing should not be reused. Equipment should be inspected to make sure it's in good condition with intact O-rings to avoid communication between various water-bearing zones within the same boring. Operators must be certified, and all permit approvals must be on site. And where the borehole extends to a depth greater than 25 feet, the borehole must be properly sealed. However, since these direct push boreholes don't generate cuttings, sealing with grout is recommended in areas of contamination even at less than 25 feet. Next slide. So the aqueous sampling section goes on to discuss other types of sampling, including wastewater. This section did not change from the previous version of the manual. Basically, for sampling for wastewater, which would include influent and effluent sources at a treatment facility, you can either conduct manual sampling or automatic sampling with various types of automatic sampling devices that can either collect discrete or composite samplers. This figure shows an example of an ISCO sampler, and these devices can also sometimes be adapted for use with surface water sampling. Next slide. So section 5.3.3 is surface water and liquid sampling equipment. This includes any fluid body, flowing or otherwise, whose surface is open to the atmosphere. So the examples or the technologies of surface water sampling equipment are listed here, and the circled ones are the ones that were added. The majority were from the previous version of the manual. So the additions are the POSIS, or Polar Organic Chemical Integrative Sampler, and the CLAM, the Continuous Low-Level Aquatic Monitoring. So the POSIS is depicted here, and it's an example of an integrative passive sampler. They're a way to monitor the concentration of organic contaminants in aquatic systems over time. The POSIS sampler consists of multiple stacked sampling discs mounted on a support rod. POSIS samplers can also be used in monitoring wells in theory, but they can be, the configuration would have to be different to fit. The CLAM is a solid phase extraction sampler that can be used in various aquatic environments. It weighs about 2 pounds with a rechargeable battery and can actively sample water for up to 36 hours. The CLAM media is sheathed in a micro glass fiber matrix and kept in place with encased shell. There's a pump with a calibrated flow rate. One issue that might be encountered is it can clog if there are high suspended solids. Next slide. Section 5.3.4 covers containerized liquid sampling equipment. This addresses the sampling of both sealed and unsealed containers of sizes varying from drums, and it has the same list as the previous version of the manual. Other sampling devices which may be considered appropriate, including the Bacon Bomb, Chemerer, or a weighted bottle sampler, previously explained in section 5.3.3 of this chapter, can also be used. It should be considered the location of the container, the location and size of the opening, and health and safety when choosing the type of sampler. All horizons present in the container should be collected. Next slide, please. So section 5.4 covers non-aqueous sampling equipment. This slide shows the list, the overview of this section, listing out the different types of sampling equipment and the subcategories. There were no changes to the list of sampling equipment. In general, when collecting soil samples, there are two different categories of devices, basically a means to collect a core and then separately to collect a sample. So for example, a soil coring device would collect your soil core, and then an on-core sampler would be used to collect a VOC sample from that soil core. An appropriate sampling device for the constituent being sampled for should be used. For VOCs, soil disturbance must be limited, therefore a bucket auger should not be used, and instead a coring device should be used to collect the initial soil core for sampling. Also, with respect to VOCs, soil should be logged after collecting samples, and an option could also be to collect encores from every 6 inches of core before determining which would be shipped, but that would involve additional cost. The most important aspect of non-aqueous sampling is to retrieve a representative sample of all horizons present. Effort should be made to maintain sample integrity by preserving its physical form and chemical composition. Next slide, please. So of note, there are 2 tables in this section, table 5.3. They can be helpful in choosing a sampler type for sediment samples, and then table 5.4, our samplers recommended for various types of waste. This lists the types of waste and limitations of each sampling device. These figures are examples of sediment samplers used to grab a sample, and there is also a picture of a waste pile sampler, which is one type of sampler for solid waste. So this concludes Chapter 5, Sampling Equipment. The manual goes into much more detail about the topics that were outlined, and only a small part was discussed in the interest of time. Chapter 6 goes on to discuss sampling methods. Thank you.
Thank you, Catherine and Greg. Next, we have Carrie Brookhouse, Greg Giles, and Crystal Peruzic presenting Chapter 6, Sample Collection.
Hi, good morning. I'm Carrie Brookhouse, a senior consultant with BSI America Professional Services and an LSRP. I will be covering sections 6.1 through 6.8. If you want to go to the next slide. Chapter 6 covers the sample collection of multiple sample matrices as detailed here in sections 6.2 through 6.11. As I mentioned, I'll be covering section 6.2 through 6.8, and then Greg will take over and finish out the chapter. Next slide. As noted in Chapter 5, site conditions, sample matrix, and your analytes to be assessed will dictate the type of sampling equipment and your methods used. Chapter 6 provides both general steps that are going to be followed regardless of the sample matrix and an overview of how to sample the various matrices using a variety of equipment and sample methods. And again, as already noted by Catherine, our list within the manual is not exhaustive, but covers current industry trends. You'll also find within Chapter 6 links to additional resources for more information. Next slide. Section 6.2 covers soil sampling. There were no substantive changes to this chapter, but there were some things we wanted to highlight. First, it's recommended that you log your soils after you collect your sample to minimize loss of volatiles. If you're using a drilling method that has the potential to increase temperature of the soil core, it's recommended that you collect soil core temperatures and note those on your soil log. If you pull up your soil core and find that you don't have enough recovery or volume in the interval that you plan to sample, it's recommended that you drill an adjacent hole so that you can get the material or the volume needed for that specific interval depth. And again, collection of VOCs from hand-cleared holes using high-pressure air or water is not recommended. Section 6.3 covers rock coring, and in this section, sonic drilling method was added. Section 6.3.1.3, sonic drilling method is a dual casing advancement technique employing an inner primary core barrel and related drilling casing, and an outer override secondary cutter head and associated drill casing. Next slide. Section 6.4 covers direct push. Direct push technology allows for the collection of segmented soil cores and allows for the ability to visually determine your geological data. It
definitely is recommended that you're using a high pressure hot water cleaning to decontaminate your direct push sampling equipment in between your locations so that your data is not influenced by unwanted variables. Also added to section 6.4 were additional details on the use of sonic drilling to collect soil samples, including ways to mitigate the potential for temperature increases. It's also recommended that when collecting a sample from a sonic core that you use a rigid inner liner to hold the soil core together during removal from the core barrel. Additional site characterization techniques, many of which use direct push technology, have been added to Chapter 7, which will be discussed later. Next slide. Section 6.5 covers the sampling of containerized material. Containers can vary in type from a drum to a tanker truck. So in that, health and safety is of utmost importance. Things you should consider when sampling containers are the container staging, identification, opening, and next slide. Section 6.6 covers the sampling of waste and beneficial reuse piles. Again, there's a variability of piles, so they do not allow for an outline of exact sampling procedures, but things you should consider would be size, shape, material characteristics, and access. Here's a list of tools that are often used when sampling piles. Again, it's recommended if you're not using a disposable sampling equipment that you do decon each of these pieces of equipment between sample collections. Section 6.7 covers superficial sampling, and this is related to various surfaces like floors or counters rather than your surface soils. Next slide. Section 6.8 covers surface water and sediment sampling. There were no procedural changes made to this section. However, it was revised to align more closely with the ecological evaluation technical guidance. And again, health and safety is a priority when working near water. Section 6.8.1 specifically states personal safety associated with surface water and sediment sample collection will always be the first priority when selecting the appropriate equipment and related procedures. Things to consider when you're preparing your sampling plan for surface water and sediment sampling. You want to take into consideration the water body's physical characteristics, for example, the size, depth, and flow. For non-flowing water, you may also want to consider temperature, as if it's a deep location, you could have different temperatures at different depths. So that would potentially require multiple samples. Non-aqueous samples should be accompanied by laboratory analyzed total organic carbon and particles grain size for each sample. I think pH, yes, and pH. Sampling should proceed from downstream locations to upstream locations. If surface water and sediment samples are to be collected at the same time, they should be co-located. And again, decontaminate or dispose of your sampling device before taking the next sample. And then I think next slide should be Greg. Thank you very much.
Good morning. My name is Greg Giles, and I'm a geologist in the Bureau of Groundwater Pollution Abatement within the Contaminated Site Remediation and Redevelopment Program. Today, I'm here to present information on Section 6.9 of Chapter 6, Groundwater Sampling. This section of the manual is now approximately 85 pages long, so my presentation will primarily focus on additions and changes to this section. During this presentation, I will be using the term well intake interval. This term incorporates the concept of both the well screened interval and the well open bedrock borehole interval. This term is now used in section 6.9 to reduce the number of times both situations need to be listed. Please note that during my presentation, I will be referring to the low flow purging and sampling method simply as low flow. Given the linked relationship of some of the issues that I will be discussing, there will be a certain amount of duplication in my presentation. To provide clarity and stress the importance of some presentation material, some slide text will be read verbatim. Next slide, please. This slide presents 3 observations that DEP used in updating section 6.9. How you sample, that is the sampling method. When you sample, that is the depth to water at the time of sampling. And where you sample, that is the depth of sample collection in the well, may affect the sampling results. These observations are likely the result of the complex interaction of site geology, site hydrology, and contaminant behavior with respect to the location and depth of the well intake interval. We are talking about the interaction of variables such as the site hydraulic gradient, is it upward or downward, and how strong is the gradient? The solubility and density of the contaminants of concern. Are we looking at L-NAPLs or D-NAPLs, or just dissolved phase concentrations? And changes in permeability of the aquifer material, both vertically and horizontally. Are there restrictive layers or dominant bedrock fractures that are affecting contaminant migration? In simpler terms, these observations are likely due to the spatial relationship of the well intake interval to the groundwater plume. Next slide, please. This is a real table of historic groundwater sampling results that was submitted to DEP. The name and location of the site have been removed for discussion purposes. On the left side of the table, you can see that the data is identified as being from a water table well screened 12 to 27 feet below ground. On the left side of the table, there's a column titled Sampling Method. This column is marked by a blue arrow. As you can see from the table, samples were collected from this well by the volume averaged method and the passive diffusion method. Please note the water quality results for PCE, TCE, and CIS12DCE highlighted in yellow. When you compare the highlighted sampling results to the identified sampling method, the sampling results from the polyethylene diffusion bag samples are notably lower than that generated by the volume averaged method. The effect of changing the sampling method was confirmed when switching back to the volume averaged method resulted in an increase in the highlighted compounds. Based on observations like that shown on this table, DEP is now recommending that tables of groundwater sampling results key the sampling results to the method of sample collection. Where possible, tables of historic groundwater sampling results should be modified to list the method of sample collection. Next slide, please. This is a slide showing changes in depth of water with time. The data is from a U.S. Geological Survey water table well in Morris County, New Jersey. The date of the measurement is expressed on the horizontal axis and the depth to water is expressed on the vertical axis. The data represents continuous monitor level monitoring with the circles representing field visits to the well. This well shows a seasonal pattern of changing groundwater depth. As illustrated in this figure, in New Jersey, the water table is frequently highest in the spring and lowest in the late fall to early winter. Next slide, please. While seasonal changes in water depth are common, shorter periods of significant drought or precipitation can significantly affect the depth to water. As an example, a late season hurricane can raise the water table when it is usually declining. This issue mainly affects water table wells. The location of the well can affect the range of water level variation. Wells installed in higher areas generally have a greater range of water level variation than wells installed in lower lying areas. Next slide, please. Knowing the water levels may vary in seasonal patterns, let us look at this table correlating sampling data on the horizontal axis, and contaminant concentrations on the vertical axis. This is an actual table that was submitted to DEP that documents the water quality in a specific well from 1999 to 2013. Sampling times on this table are generally around early January and early July. PCE and TCE concentrations on the left are shown in a logarithmic scale. For clarification, I have highlighted select sampling events occurring near January 1st. The samples collected in the January sampling event frequently have lower contaminant concentrations than the samples collected in the July sampling event. The variation in contaminant concentrations can be over an order of magnitude. This table shows that your sample results may be affected by the time of year that you sample. Based on this observation, DEP is recommending sample results be keyed to the date of sample collection. Next slide, please. This is the same table that we looked at a couple minutes ago. This time I want to draw your attention to the passive diffusion bag sampling events of March 2019, highlighted by the blue arrow. During that sampling event, diffusion samplers were set at well depths of 17 and 24 feet in an effort to vertically profile the water quality in the well. Please note the difference of cis 1,2-dichloroethylene and vinyl chloride between the two samples. These results are highlighted in yellow. The passive sampler set at the depth of 24 feet showed notably higher concentrations of 1,2-dichloroethylene and vinyl chloride than the sampler set at 17 feet. Next slide, please. Documenting the depth of sample collection. The data shows that the depth of sample collection may affect your sample results. The depth information collected should be from ground surface. Based on this observation, the depth of sample collection should be listed on field sampling sheets, and it is recommended that sampling results be keyed to the depth of sample collection. Next slide, please. On this table, columns are provided that allow for the documentation of sample data, sample method, and sample depth. If turbidity measurements were collected, an additional column should be added to the table for that information. DEP recommends a similar format be used to present the requested information. Next slide, please. The aforementioned observations have led to the addition of specific sampling guidance, which is presented in the policy section listed as 6.9.1.4. Application of the LSRP's best professional judgment provides a mechanism for the guidance to be modified or bypassed. When this action is taken, language supporting that action should be provided. I will now present some of the policy guidance outlined in this section. Previously generated well information such as well yield and depth of water measurements should be brought to the well during sampling events. Knowing the well yield will facilitate appropriate purging of the well, and knowing past depth of water measurements will act as a check on the collection of new depth of water measurements. Since volume average sampling generates a sample that represents a larger portion of the aquifer, DEP recommends the first two sampling events for a well be performed by the volume averaged method. To account for seasonal variation, the requested second sample should be collected a minimum of 90 days after the first sample. Next slide, please. When a permanent well is being sampled for well or site closeout purposes, that is, the sampling results are intended to be used to justify an aspect of site closure or abandonment of a specific well, DEP recommends the well be sampled using the volume averaged method. As just stated, this action is being recommended because this method generates a sample representing a larger portion of the aquifer. Aside from initial and final well sampling, other sampling methods may be used. Since temporary well points are frequently installed in areas of limited or no pre-existing groundwater data, DEP is recommending that temporary well point sampling be performed by the volume averaged method when possible. Next slide, please. Where volatile organic compounds are a contaminant of concern, and the well has never been sampled by the volume averaged method, DEP is recommending that the well be sampled by the volume averaged method during the next sampling event. DEP is recommending that a volume average sample be collected so that the results can be compared to that of other sampling methods. Next slide, please. If only sampling for turbidity-sensitive compounds, the recommendation to use volume average sampling for certain sampling events does not apply. In this situation, the use of other sampling methods that may reduce or limit sample turbidity, such as low flow or passive sampling, may be used at any time. Next slide, please. DEP is recommending that the first 2 sampling rounds of a given well include the measurement of the water quality indicator parameters. The point here is to generate well-specific chemistry data during the initial sampling events. Documenting the water quality indicator parameters is critical to the development of the site conceptual model and to the design of groundwater remedial measures. When electrically powered submersible pumps are used for the collection of groundwater samples that will be analyzed for temperature-sensitive compounds, such as VOCs, the water temperature of the purge water should be monitored and recorded. Increases in water temperature increase the potential for VOC loss during sample collection. This is because increases in the temperature of the volatile organic compounds increases their vapor pressure, which is the force driving the migration of the volatile compound from the liquid phase to the vapor phase. Where undesirable increases in discharge temperatures are detected, actions should be taken to address that issue. Next slide, please. Where a well contains greater than 5 feet of water in the well intake interval, a sampling method other than volume averaged is planned. DEP recommends that vertical profiling be performed to determine if the water quality within the well intake interval is stratified. It is recommended that the profiling be performed during the first round of non-volume average sampling. This recommendation is well specific. Where a change in the sampling method results in contaminant concentration changes beyond normal analytical variation, it is recommended that the sampling method that produces the higher contaminant concentration be used. Next slide, please. Where the sample results will be used to make a regulatory decision, that is, an initial exceedance or well closeout, sampling methods other than the volume average method can be used even if they generate lower contaminant concentrations. Where a sampling method is being used that has been documented to produce a lower contaminant concentration, that observation should be footnoted on tables of groundwater results. The footnote should be well specific. Next slide, please. To help steer you through the policy issues related to the sampling method use, DEP has developed a groundwater sampling decision tree that has been added to the manual as Figure 6.10. You start at the top and work your way down by answering the statements that are worded as questions. This figure is provided as a handout linked to this training event. Next slide, please. A new section titled Technical Considerations has been added to the manual. This section includes discussions on issues that DEP feels are important with respect to development of the sampling plan and the collection of the groundwater sample. Shown here are a few items from that section that will be discussed. Next item, please. Next slide, please. One of the main goals in a remedial investigation is the vertical and horizontal delineation of the contaminated groundwater. In the pursuit of that goal, monitor well depths target zones of groundwater contamination, not zones of elevated well yield. That action results in a large percentage of monitor wells being installed in shallow, fine-grained, low permeability material. These wells frequently have low recharge rates, making them very susceptible to water level drawdown during well purging. Drawdown of the water level in the well intake interval can lead to a loss of volatile organic compounds and the precipitation of some dissolved metals. The greater the level of drawdown, the greater the potential for VOC loss. Purging wells at rates above their recharge capacity can produce undesirable levels of well drawdown, such as purging a well to dryness. Next slide, please. To reduce the potential for undesirable levels of drawdown to occur, the well recharge rate should be accurately determined before the well is sampled. Knowing the well recharge rate allows purging equipment with appropriate capabilities to be used. To limit drawdown, the water level in the well should be monitored and recorded during the purging process. Where an undesirable rate of water level drawdown is occurring, the purging rate should be changed to prevent undesirable levels of drawdown from developing. In water table wells, the drawdown should be limited to the extent practicable. For wells with completely submerged well intake intervals, drawdown to the top of the well intake interval is acceptable. Next slide, please. Elevated sample turbidity can result in a biased high groundwater sampling result for compounds that have an affinity to bind to soil. Examples include the testing for metals, PCBs, pesticides, herbicides, polyaromatic hydrocarbons, and some PFAS. Where groundwater testing of turbidity-sensitive compounds is performed, it is recommended that turbidity measurements be collected and recorded throughout the well purging process, and a turbidity measurement taken at the time of sample collection. The turbidity measurement collected at the time of sampling should be keyed to the sampling results where the results are presented in tables. Linking sample turbidity to the sampling results will allow for a better assessment of the sample results. Next slide, please. Where the water removed from the well is turbid and turbidity-sensitive compounds are a contaminant of concern, it is recommended that measures be taken to reduce the turbidity of the water in the well. These measures may include redevelopment of the well, purging the well at a lower purge rate, and using a no-purge sampling method such as a grab or passive method. Next slide, please. To reduce the potential for well drawdown problems to occur during sampling, DEP recommends that the recharge rate of each well be accurately determined. The lower the well recharge rate, the more important the need for an accurate recharge rate to be determined. This is because wells with low recharge rates are much more prone to develop undesirable amounts of drawdown during well purging. It is recommended that the well recharge rate be determined during well development or shortly thereafter. The determination of a well recharge rate should occur before the well is sampled so that this information is available to the sampling crew. For existing wells where this information has not been determined, it is recommended that actions be taken to determine the recharge rate of the wells. It is recommended that the well recharge rate information be added to tables that summarize well information. This table could then be brought to the field to facilitate sampling. Knowing the recharge rate of the wells should facilitate the development of sampling plans and enable purging equipment with appropriate pumping capability be brought to the site during the sampling event. Next slide, please. DEP is recommending that the measurement of the water quality indicator parameters be performed during the first two sampling events for each well to establish the groundwater chemistry at that location and depth. Knowledge of the water chemistry is critical to the development of the site conceptual model and understanding of the fate and transport of the contaminants of concern and the design of future groundwater remedial actions. The important link to be made here is that since DEP is recommending that the first two rounds of a given well be sampled by the volume averaged method, and DEP is recommending that the water quality indicator parameters be collected during the first two sampling rounds. By default, the first two rounds of volume average sampling should have the water quality indicator parameters measured and recorded. When conducting low flow sampling, the collection of the water quality indicator parameters is always needed, as that information is critical to the performance of that method. Per NJAC 7:18, the samplers must be certified by the samplers who are collecting the water quality indicator parameters must be certified by DEP's Office of Quality Assurance. Next slide, please.
Hello, everyone. It's time for our first poll question of the day. Poll question number 1 will be launched. You should answer the question in the window that launches and not in the chat. Make sure you're answering the poll questions if you're seeking CECs for today's training. That's how we track that you are here. The question is, how, when, and where you sample groundwater can impact your sampling results? A, true, or B, false? The poll window should have launched. If you don't see the pop-up, check behind the window you have open. We'll give you about a minute to answer the question. All right, and the answer is A, true.
All right, thank you very much, and we're back. Guidance on the vertical profiling of water quality now has its own section. DEP recommends vertical profiling be performed to determine if there is a contaminant concentration stratification in the well intake interval. The profiling should be performed on a well prior to using any sampling method other than volume averaged on that well. The profiling only needs to be performed once on a given well before using a sampling method other than the volume averaged method. Next slide, please. The depth of sample collection should be documented. The rationale for the chosen sampling depths should be discussed in the report that contains the sampling results. Where contaminant concentration variation is detected, it is recommended that future sampling be biased to the depth showing the higher results. Where future sampling does not target the highest concentration, this action should be documented and an explanation provided. Next slide, please. If the results from the vertical profiling show similar contaminant concentrations, it is possible that the similarity in sampling results is due to vertical flow in the well. Section 6.9.5.5 discusses possible causes of vertical flow and ways to determine if it is occurring. Next slide, please. DEP has expanded the recommended use of polyethylene tubing for sampling and has added section 6.9.6.3.1 to discuss this issue. In association with this section, table 6.14, shown here, has been added. This table outlines a hierarchy of tubing quality, which is linked to recommended use. The reference to tubing quality means the potential of the tubing composition to negatively affect the contaminant concentration of the water in contact with it. Tubing quality decreases from top to bottom in the table. Next slide, please. DEP is defining a low-yield well as one that has a sustained recharge rate of less than 100 milliliters per minute. These wells are prone to develop drawdown problems during purging, and the long residence times in the well may lead to the quality of the water in the well not being representative of the surrounding aquifer. So there may be a downside to any method used to sample these wells. Next slide, please. If you think you have a low-yielding well, confirm that the well has a sustained recharge rate less than 100 milliliters per minute and that the well was adequately developed. Provide supporting documentation. In this situation, modification of a sampling method may be needed. All modifications should be documented. To address this problem, DEP recommends that samples be collected by multiple sampling methods during a common sampling event. The results of that sampling event should be compared to determine what method generated the highest contaminant concentration. Next slide, please. The sampling methods can be roughly grouped into several categories, the main ones being volume averaged, low flow, and no purge. No purge itself is then subdivided into grab and passive. Examples of grab would be a snap sampler or a hydrosleeve. An example of a passive would be a regular or dual membrane polyethylene diffusion bag. Next slide, please. Volume average sampling is a method where typically a minimum of 3 well volumes of water is purged from the well prior to sample collection. The sample collected may represent a larger section of the aquifer because of the greater volume of water removed from the well. This method generates the most purge water. Pump depth and water level drawdown in the well should be monitored and recorded. DEP recommends the same pump and tubing be used for purging and sampling. Next slide, please. Where the water level is above the well intake interval, action should be taken to make sure that the sample does not contain stagnant casing water. Drawdown to the top of the well intake interval is acceptable in this situation. Where the casing water is isolated or removed, the purge volume can now be recalculated based on the volume of water in the well take interval. Next slide, please. Low flow represents a method involving purging the well at a relatively low purge rate that minimizes sample turbidity. The water quality indicator parameters are measured and recorded during purging. When variation of the water quality indicator parameters has stabilized, the sample can be collected. The stabilization criteria for each parameter is defined in the manual. This method has a lower potential for drawdown issues due to a lower pumping rate. It has a lower potential for turbidity issues, since it should induce less stress on the well intake interval, and it generates less purge water. Next slide, please. Additionally, the sample may represent a smaller area of the well intake interval than a volume average sample. It is recommended that the water quality in the well be vertically profiled before use of this method. This method is not recommended for initial or closeout sampling of a well unless only sampling for turbidity sensitive compounds. Next slide, please. This is no purge grab sampling method. This method generates no purge water. The sample results only represent the depth or zone of the collected water. It is recommended the water quality in the well be vertically profiled before use of the method. And due to the limited zone of capture by these devices are not recommended for initial or closeout sampling of a well unless only sampling for turbidity sensitive compounds. Next slide, please. Passive sampling is a type of grab sample dominated by the use of thin membrane diffusion bags. To be detected, the contaminant of concern must be able to cross the device membrane. There is no purging, so the device only picks up contamination directly in contact with it. The sampling devices are filled with laboratory-supplied clean water prior to deployment. Use requires the device to be placed in the well at least 2 weeks prior to device retrieval. Certain compounds or devices may require longer deployment periods. Next slide, please. The sampling device should be placed in the well intake interval. The sampling device must remain completely submerged when in the well. It is recommended that the water quality in the well be vertically profiled before use of this method. And due to the small zone of capture by these devices, they are not recommended for initial or closeout sampling of the well unless only sampling for turbidity sensitive compounds. Next slide, please. This slide illustrates how samples collected by different sampling methods may represent a different footprint of the aquifer. As depicted, the volume average method on the left may produce a sample representing a larger footprint of the aquifer. The passive method on the right shows that the sample only represents the water that is in contact with the sampling device. While not depicted, a grab sample would most align with the passive sampling scenario on the right side, since it is a no-perch method. As depicted by the arrows, the direction of groundwater flow is from left to right. The size of the arrow is a representation of the material permeability. The larger the arrow, the greater the permeability of the listed layer. The color range on the bottom shows how the footprint of the sample may change with continued purging of the well. Generally, as the purge time increases, the footprint the sample represents increases. Next slide, please. DEP no longer supports the 1994 Alternative Groundwater Sampling Techniques guidance, so guidance on temporary well points is now taken from the updated Field Sampling Procedures Manual. The 2018 revision of the well construction regulations increased the allowable installation time for temporary wells from 48 to 72 hours. The increased time facilitates the performance of additional tasks on these wells, such as well development, well surveying, downhole logging, and short-term assessment of groundwater depth. Next slide, please. DEP recommends temporary well points be developed prior to sampling. Development could be performed using small diameter bladder pumps, initial pumps, or peristaltic pumps. Since temporary well points are frequently installed in areas where the groundwater quality is unknown, DEP recommends collecting the samples by the volume averaged method, so the sample represents a larger area of the aquifer. The volume of water removed during the development of a temporary well can be included in the volume needed to be purged by the volume averaged method. Next slide, please. This is a picture of the updated construction for a flush mount well completion. Flush mount boxes are prone to water infiltration from rainfall and surface ponding. Where this happens, the interior space of the well box can fill with water. If an expansion plug on the interior well casing is missing or not watertight, water can drain into the well itself. To address this issue, Figure A 6.3 has been modified to recommend the installation of a drain that channels water from the interior of the well box to the surrounding soils. The drain should be of sufficient diameter that it does not clog with time. The drain should extend into the surrounding soils to an extent that the drain is not affected by the addition of the cement used to anchor the flush mount box. In review, DEP has shown that how you sample, when you sample, and where you sample can affect your sampling results. So information like sampling method, sampling date, sampling depth, and sample turbidity should be key to the sampling results. To facilitate appropriate purging of a well and reduce the potential for undesirable levels of drawdown from occurring, it is recommended that an accurate recharge rate of each well be determined. It is recommended that this information be with the sampler during the sampling event and included in tables of well construction information. Since the volume average sampling method produces a sample that represents a larger zone of the aquifer, it is recommended that the volume average sampling method be used for initial and closeout sampling events. Conversely, since the low flow, grab, and passive methods generate a sample that may represent a much smaller zone of the aquifer, it is recommended that a well be vertically profiled before a sampling method other than the volume averaged method is performed. There is an underlying theme in the material that I presented, and that is documentation. Where relevant, DEP is looking for documentation of sample method, sample date, sample depth, sample temperature, sample turbidity, initial depth of water, well recharge rate, purge volume, variation in pump depth during purging, variation in water level drawdown during purging, and residency time of the sampling device in the well. This concludes my presentation. Thank you.
Okay, thank you very much, Carrie and Greg. Up next, we have John Bracken to discuss the updates to Chapter 7 Field Analysis.
Good morning, everybody. As mentioned, I'm John Bracken, a senior consultant LSRP with Verdantis. This portion of the training session will include chapters 7, 8, and 9. Next slide, please. As mentioned, The work group for Chapter 7, 8, and 9 includes the list of folks here under the direction of Crystal. I will be discussing Chapter 7, which was posted on December of 2023. Next slide. Chapter 7 focuses on streamlining the data collection, the roles, applications, and choosing appropriate field analytical instruments, and it also talks about the quality assurance requirements. Most of the Chapter 7 updates include characterization tools and some direct read field instrumentation. Next slide. The breakdown of Chapter 7 includes the field instruments, application of field instruments, choosing appropriate field analytical instruments for your contaminant investigation, field screening instruments, characterization tools, the data quality levels for implementation, and then the quality assurance requirements. This chapter is approximately 25 pages. Updates to equipment are ongoing, and we've included some of the general industry standard equipment. However, new equipment and updates are constantly ongoing, so there may be changes, but again, as some of the other previous chapters were discussed, it's all about documentation, and the investigator will need to justify equipment used, the intended use, and then the justification of the data. Next slide. The list here includes a bunch of the field instruments and characterization tools that we've updated in the chapter. Majority of these most folks have seen or used in the field. Some folks may have not used some of the other more advanced pieces of equipment that have been updated in recent years. Care should be taken to understand the types of equipment that are being used, their limitations, and then the types of contaminants that are being investigated. What is the intent of the field equipment? Is it screening for absence presence, delineation, remediation, confirmation? And then what media are you sampling for? Some of the equipment that's listed here can be used for soil and groundwater, as well as NAPL, and including specific types of NAPL, whether they're L-NAPL or T-NAPL. Next slide. Examples here, some of the key updates. We included handheld units. Most folks are probably familiar with PID, the photo ionization detector, as well as an FID, the flame ionization detector, or an OVA, which is organic vapor analyzer. Included in here as well is a portable GC, which can obviously provide some more detailed results, as well as the XRF, which is the X-ray fluorescence used for metals. Most of these provide semi-quantitative results, and again, note that the portable GC and the XRF can provide quantitative results with compound-specific outputs. Next slide. With any piece of equipment, you're going to have advantages and limitations. Most notably with a lot of the handheld stuff, they're mobile and lightweight. They also provide quick results. Limitations on any of these equipment is rental costs. Most people don't own them. Some people do own some of these various pieces of equipment, but you may have to rent them. A lot of them have limitations with weather durability, and then the outputs on the quantitative, semi-quantitative results, whether you're looking for total concentrations or individual compounds. So you just have to understand the limitations of each. Next slide. Additional pieces of equipment that were added that some folks may have used are the TPH, total petroleum hydrocarbon, and the petrohydrocarbon analyzer kits. Next slide. These are the PCB kits that are also have been added. Some have an assay component to it, and others are the standard white kits that have to be sent out for analysis. Next slide. Advantages and disadvantages or limitations of the field analyzer and assay kits. They provide results in a relatively short amount of time. They're not instantaneous. However, they do provide results faster than sending samples out to a lab. And it allows you to make field decisions to expedite your site investigations, remediation, or waste disposal. They are relatively easy to use. However, you do need to be familiar with the operation of each. The limitations on some of these pieces of equipment is assays require extraction. It's not an instantaneous reading. The kits can be temperature sensitive or photosensitive. And then they also, some of the kits require an analyzer. So you need a workstation to be out of the weather, or some sort of operational area or power to run some of the analyzers. Next slide. Some of the more involved pieces of equipment that some folks may have used is the membrane interface probe, the MIP, or the laser-induced fluorescence, the LIF. There's also a dye LIF as well. These pieces of direct push equipment are quite involved, but they do have a very detailed output. They typically require a subcontractor. They do require some significant space and clearance. And some of the pieces of equipment, while their recommendations in here, some are proprietary, and you do need to talk to specialized contractors. Next slide. As part of kind of the overall direct sensing equipment, the examples that are provided here are from left to right, can provide outputs in both 2D and 3D, as well as provide graphical results. One of the things that's beneficial about doing these profiling type tools is the fact that you can add multiple different sensors with these pieces of equipment to target specific compounds and then generate a specific output. Such as with MIP, you can add in a hydraulic profiling tool, which can provide you with hydraulic conductivity. You can do hydrogen-specific detectors, which is an XSD, and that specifically targets halogenated compounds like chloroform. You can do an ECD detector, which is an electron capture detector, which focuses on chlorinated solvents. And then at the same time, you can also do CPT, which is a cone penetrometer, and you can get some physical properties about your soil types. But just recognize that there's a lot of tooling that can go into this, and you have to understand the application, what compounds you're targeting, and then the overall approach for your project. Next slide. The advantages and limitations of this type of direct sensing equipment include being able to detect both in soil and groundwater, as well as NAPL, separate phase. As I mentioned before, you can have the graphical and 3D outputs, which can help you with your site conceptual model. These also can be provided, as I mentioned, with the various different direct push tooling equipment that can give you some supplemental details about lithology or hydraulic conductivity or chemical specific outputs. So understanding what your desired goals are is key. The field limitations on these is that there is a significant cost. Again, that's relative. However, you can have some expedited characterization, but just understand that field equipment and the cost. With a lot of the direct push technology, there is a limitation on lithology. So you do need to kind of generally understand the application in which you intend to use these. And they do require either an understanding of operating the equipment or various licensing, depending on the depth that you're targeting. And with all of this, it does require some space and staging to have a work zone. The evaluation, for the most part, is understanding your project, what your goals are, and then again the intended use. Next slide. With all of these pieces of equipment that we just mentioned, realist is the data quality objective levels. There's several quality levels, DQO1 through 3. Primarily with preliminary and field screening, DQO level 1 is your screening data, typically not compound specific or quantitative. It's PID, FID. With your DQO level 2, you have effective data when you can actually verify a portion of it with lab analysis, and you get data generated with EPA approved methods. Next slide. On the data quality level 3, This is the meticulous or definitive data. These are the lab analyzed samples, and methods are used to determine exact concentrations and identify the actual compounds. And these are performed in accordance with QA/QC requirements for the tech regs, and you get data deliverables and quality control, quality assurance samples. Well, the last section of the data quality objective is what's called state-of-the-art data, and that's where you're going to have, say, a compound or a particular site that has a unique situation in which you'll have to develop a specific method for your analysis. Next slide. On the quality assurance requirements for the field indicating and characterization tooling, DQO level 1, the screening data really should only be used as an indicator. So mentioned before, absence, presence, with identification such as with a PID or something that's a total organic vapor analyzer, which you just get a total number, not compound specific, and there's no actual laboratory data generated. On the DQO level 2, the effective data are intended for rapid delineation. You can use the field analysis to generate semi-quantitative or semi-qualitative results, and then you can achieve kind of a high degree of reproducibility where you collect your field analysis and then verify a handful with actual laboratory analytical data, and then you can kind of create an overall understanding of the confidence in the sampling methodology with your field characterization tools and verified by the field instrumentation with analytical results. Next slide. On the DQO level 3, the definitive data, this is the most reliable and reproducible, generates laboratory analytical results with full or reduced data deliverables in accordance with Appendix A of the tech regs. That's typically what most people are accustomed to. But again, looking at what your intended use is, you may not necessarily need to do DQO level 3 for your initial stages of the project, but you do need to be cognizant about implementing data quality level 3 for post-remediation and submissions for your final remedial action report or closing out, remediation areas definitively. On the state-of-the-art quality assurance, it's a little bit more involved. The methods are going to be developed for a particular site or contaminant. They may be variable with the deliverable requirements, and the methods are going to have to be developed by the laboratory or the individuals that are performing the analysis, and you're going to have to work with the Office of Data Quality, NJDEP, and get approval, and then that's ultimately going to need to be updated and included in your site-specific QAP, which then, of course, you'll have their quality assurance and quality control that you'll be able to implement for the project duration. With that, that is my last slide. Thank you very much.
Thank you, John. Next, we have Mike Gagliano presenting on Chapter 8, Geophysical Techniques.
Cool. Good morning, everybody. My name is Mike Gagliano. I'm a geophysicist with the NJDEP Geological and Water Survey, which is Bureau of Water Resources and Geoscience, and I'm going to be speaking about Chapter 8, which is the Geophysics chapter. Next slide. So the outline of the chapter is shown here. So it covers both surface and borehole geophysical techniques at the end. Next slide, please. Like I said, I'm going to cover both surface and borehole geophysical methods today, which are cost-effective, and for the surface techniques, they're non-intrusive tools for remediation sites. They're useful for contamination and groundwater mapping, USTs, monitoring well placement, hydrogeologic frameworks, and can generally be rapidly deployed in the field to collect high-resolution data. Next slide, please. All right, so key updates, which weren't many for this chapter. Most of the key updates were rewriting sections to incorporate advances in the majority of the equipment and techniques, which went from analog to digital, using multi-channel data collections, collecting data with computers, access to super accurate GPSs, etc. So since these changes particularly didn't affect the theory of the method and how it works, it was decided that I was going to briefly go over each method and provide some data examples to give you an idea of what some of these look like and how they might be used. Next slide, please. And so here's a common list of applications for surface and borehole geophysics. These are all listed in the manual, so I'm not going to sit here and read them. But on the next slide, I just want to briefly discuss determining which method to use. So next slide, please. All right, so the first thing you need to take into account here when you get to a site to determine geophysics is, the target. So what are you trying to find, right? So is it conductive? Is it magnetic? What's its anticipated depth, et cetera? So that's number one. The geology, sometimes we're using geophysical tools to map geology, but still, the more data you can ascertain beforehand, the better. So always look for, as much geological data as you can find. So the site infrastructure is important, especially for some of these methods. For example, is there metal fencing nearby? Is there overhead or buried power lines? Other utilities? Is there vehicles parked around? All that stuff plays a part in which method you might choose. And then, how much time you have, right? So often using two of these geophysical methods or more in tandem can provide better results, more definitive results. However, this is going to take longer, right? So, which is going to add to the cost and all that stuff. So these are all things to consider when picking which one of these methods to use. So next slide. All right, so talking about these methods. So the first thing I want to talk about here is ground penetrating radar, or GPR as it's commonly known. It's very common. It's high resolution geophysical method that uses high frequency radio waves to image the subsurface. So basically the GPR unit transmits this energy into the ground, which is then reflected off the target. So on the left here, you can see a picture of a typical, ground penetrating radar unit. So the orange box at the bottom is the transmitter and the receiver, the antenna, which is hooked up to a computer. And then typically it's on a cart like this. You can also tow it behind a car, things like that. One important note with GPR is that clay attenuates the signal really fast. So if there's clay at your site, that can cause a real problem. So some common applications are, rapidly locating buried infrastructure like UFTs and cisterns, and I actually have an example of that on the next slide. So next slide, please. So here is a typical GPR data set on the right, and you can see this is a section view, so this is into the ground, and we're reaching about a depth here, total depth of about probably 4 or 5 feet with useful data. But this is mapping an area from an abandoned building, and you can see on the data on the right there is the typical GPR data, which is called a refraction hyperbola. So it's basically usually an upside down U, and you can see that on the right here, which I circled in the dashed red line, and that actually found this huge abandoned cistern there. So this is one used for it. All right, next slide, please, which I believe is the poll.
All right, it's time for our second poll question. Poll question number 2 will be launched. Make sure you answer the question in the window. Ground penetrating radar, GPR, can be used to A, map utilities, B, find USTs, C, all of the above, or D, none of the above. The poll window should have launched. Make sure you're answering the question. We'll give you about a minute. Okay, all right, let's close that next slide, please. And the answer is C, all of the above. Back to Mike.
All right, so continuing on, next up, magnetometer. So a magnetometer is a tool for locating, ferromagnetic materials in the subsurface by detecting the ambient magnetic fields that they generate. So again, on the left here, you can see a typical magnetometer, which is mounted to a backpack, and the computer's mounted there, the GPS is mounted on there, so you can have fairly rapid data collection of an area to know what you're looking at. Again, one major limitation here is that any magnetic or ferrous material near the study site is going to cause problems. So, if there's a lot of infrastructure around, that's really a limiting factor for its use. So that being said, the common application is to look for ferrous objects or USTs. So I have an example of that on the next slide. So next slide, please. Yeah, so here's the geophysical results from magnetic survey. So this is presented in plan view here, and this is showing the total field intensity with the cool colors, so the blue and the green representing low magnetic signatures, and background level measurements, so warm colors, red and yellow, representing that. And so on the bottom left, you can see, so the bottom left is an anomaly from 2 known tanks where they were at this site. And then in the middle there, sort of between the 200 and 250 meter mark, there are 4 other anomalies, which also indicate 4 additional buried tanks that were located at this site. So, yes, next slide, please. All right, gravity. So gravity is a passive geophysical tool that measures and maps lateral changes in the Earth's gravity field, which is a function of the Earth's material density differences. And so on the left, again, is a typical gravimeter. Everything's self-contained in this case. And it's not really a limitation of gravity, but you need to have the elevation and the coordinates of the measurement spot precisely surveyed in. If the elevation's off even by a few centimeters, it can throw the data off. It's really sensitive. So again, sometimes this can take a little bit more time and add time and cost to the survey. Again, this is not particularly an LSRP thing, but some common uses are bedrock and mine mapping. So I have an example of that on the next slide. Yeah, so this is from Ringwood, New Jersey. So again, this is in plan view of an area over an abandoned mine, and you can see the area in blue here indicating a lack of gravity measurements, so indicating the void, which is showing the mine circled in the black dashed line. So next slide. All right, electrical resistivity. You may see this as ER or ERT, electrical resistivity tomography. So it's a method that injects DC current into the ground between 2 current electrodes and measures the drop of the current between 2 other potential electrodes. And from that, we can construct a resistivity profile of the subsurface. So again, here's a modern resistivity system on the left. So the yellow box is the control box, which does all the injecting of the current, which is hooked up to the battery. That is in turn connected to the multi-core cable there, which can be up to over 100 electrodes long, depending on the system. And then they are connected to the ground by stainless steel metal electrodes. So limitations of this, it's of utmost importance that the electrodes make good contact with the ground. So if you're in dry ground or rocky soil, that can pose problems. You can get around this. You can pour salt water on the electrodes, or you can put bentonite around the electrodes, or you can use 2 electrodes that are touching each other to increase the surface area. So there's always ways around this. Common applications here of electric resistivity, a lot of common applications, but saltwater intrusion and contaminant mapping, hydrogeology studies, but it can also be used for bedrock and fracture mapping. And I have a pretty neat case on the next slide for that. So next slide, please. So here's the data for this. So this is a project being worked on by the hydrogeology group at the survey, and they had some pump test data shown here by the blue circles. And that pump test data didn't particularly agree with the groundwater model they had constructed for the site. Nothing made sense, right? So we did these 2 resistivity lines here. So these are typical resistivity profiles. So these are, again, section view. So these are going into the ground. And the lighter colors, the softer colors, blue, green, are less or more conductive, less resistive, and the reds and yellows are more resistive. And so we did this here, and it was determined that with these resistivity sections, you can see the dashed lines that I have on here, that these were actually a geologic fault. And interestingly, this fault was mapped on an old geologic map, and it was used as a boundary in the groundwater model, but the fault was actually mapped in the wrong place. So when we did the geophysics here and put this fault in the right place, the pump test data all of a sudden made sense, and it matched with the groundwater model. And so it really made a whole complete picture of the site and made the hydro people pretty happy. So again, just another sort of good use case here that involves groundwater data. So next slide, please. Just should be IP. Yes. So all right. IP-induced polarization also injects current into the ground, similar to electrical resistivity, but it measures how much energy a subsurface object can store and release later. So basically, it's capacitance. So with electrical resistivity, the measurement is made while the current is flowing, And with IP, the measurement is made once the current is shut off. So IP is generally nowadays often uses the same equipment as resistivity, and so the data can be collected at the same time, or at least after the resistivity data is done. So there's a picture of the same setup on the left there. So one application of IP surveys, you can map contaminant plumes with it. So there's an example of that on the next slide. So next slide, please. So again, here's a section view of some IP data, and it's mapping a contaminant plume in a site, right? So the purple and red have a higher chargeability, and that's indicating the sort of extent of that plume. And it's probably indicating the bottom of the plume as well. Fresh water has a chargeability of around 0, which is when we get to the green color there. So it's probably mapping the plume and also possibly the bottom of the plume there as well. So some useful data here. Next slide. All right, electromagnetic or induction or EM is based on the physical principles of generating electromagnetic waves to induce electrical current flow in the subsurface, and then use that to measure conductivity in the subsurface. So on the left is a typical EM tool. This is an EM31. And so there's that long white pole, which is about 18 feet long. And on one end of that pole, there's a transmitter coil, which transmits the EM wave. And on the other end, there's the receiver coil, which picks up what happens in the subsurface. And then the recording instrument is in the center there, which you can't really see. It's behind me. But so again, mapping anything conductive, metal, things like that, but also used for tracking salt and contaminant plumes. And so I have kind of, again, another simple example on the next slide, which goes along with this picture. Yeah, so here's an example study. So where EM data was collected immediately in front of this salt storage shed and extending southeast to help basically determine the extent of the elevated sodium and chloride levels in the vicinity of the salt shed. So was the salt, leaching into the groundwater? So again, this data is in plan view, and the blue and green values indicate higher conductivities, and the orange and red values indicate lower conductivities. And the contoured data have higher conductivity in the northwest, and it decreases in conductivity as the survey continues further southwest away from the shed, which indicates at least that some of the salt in the shed was leaching into the groundwater. So next slide, please. All right, VLF, which is very low frequency. It's also an EM technique, but it's a passive technique, and it uses radio waves from ground-based military radio transmitters, which are used for navigation and communications to submarines. And so these are kind of all over the planet, and this instrument, uses the same method as the EM, but it uses those transmitters. So the transmitters generate low-frequency EM waves, and again, it can induce secondary eddy currents and electrical conductive targets. So one common application of VLF is locating water-bearing fractures, which can be used for well siting, for example, for putting your screen. And so I have an example of that on the next slide. Yeah, so again, here's a section view, so two-dimensional depth slice of some VLF data, and where you can see a conductive water-bearing fracture from the 120 to 220 meter mark, right where that black dashed line is. So again, good data to be able to set a well screen, for example. So next slide, please. All right, seismic. So I'm going to talk about seismic refraction and reflection, but seismic method involves generating a sound wave at the surface, either with a sledgehammer or with a vibrator or several other different methods, but the sound wave then travels through the subsurface layers and either refracts or reflects off those said layers. Next slide, please. All right, so seismic refraction is predicated on the fact that the generated sound refracts or basically travels along a geologic boundary for a period of time before it makes its way back up to the surface. So one problem with seismic refraction data, though, is that it's predicated on the fact that subsurface layers each have a faster velocity than the layer above it. So basically, it assumes that as you get deeper, the velocity keeps increasing. So if it doesn't, it can cause problems with hidden layers that you can't see and things like that. So, but two common applications of this, again, are locating depth of bedrock and depth of the water table, which again would be useful for siting a well, And I have an example of the former on the next slide. So next slide, please. So again, here's a typical refraction data set showing the time term inversion. So this is where, again, we're looking for bedrock here. So the interpretation of the top of the bedrock shown by the dashed black line. So again, the pink colors are slower velocities, and then as you go down, the velocities keep increasing till we get to the blue, which is most likely bedrock here, One thing to note that this, you can see the velocities change from the top of the bedrock. So it goes from red to yellow to green, which is probably indicating that the surface is a bit weathered too, if that's helpful for you. So there's an example of that. So next slide, seismic reflection. All right, so seismic reflection, it's typically used for geologic mapping and oil and gas surveys and things like that. And it's fairly difficult to interpret in the top 50 feet or so because you have the surface waves and the refracted waves and a bunch of other waves. So the data is kind of messy in that top 50 feet. So it generally has limited applications in the environmental fields since hopefully any remediation site, is not contaminated that deep. So unfortunately, I don't have any relevant data sets, but I just felt like for completeness of the presentation, I do have some data that was collected offshore New Jersey. So kind of showing its usefulness for geologic mapping. So next slide, please. Yeah, so real quick, I don't want to dwell on this, but here's an uninterpreted and interpreted seismic data sets. So again, these are 2D sections into the ground. And so this is showing a few coastal transgressions and regressions, the blue and yellow lines, and then an old buried river channel. So just, again, not LSRP related, but just kind of wanted to show a typical data set of what it might look like. So next slide, please. All right, so finally, borehole geophysics. So everything I've shown so far is non-intrusive, right, for the most part for geophysics, other than sticking an electrode in the ground. So this borehole geophysics, we need a well. But nonetheless, it basically involves lowering and raising a geophysical sonde into a well, which then measures certain properties of either the borehole fluid or the borehole formation. So some common borehole tools are shown here to the right and listed here. But we have gamma, which measures the formation radiation, which can indicate clay layers. Caliper tool, which measures the inside diameter of the well and can locate fractures. Electrical resistivity, which uses the same principle as the surface method and measures formation resistivity. We have spontaneous potential, or SP, which measures natural current flow. And we have the induction or EM tool, which again measures the same principle, uses the same principle of the surface method and measures formation conductivity, fluid conductivity, and temperature. So this is actually measuring the fluid conductivity of the fluid in the well and its temperature. There's a sonic tool, which measures acoustic properties of the rock, so kind of seismic, and this can indicate permeability, porosity. And then finally, we have an optical televiewer and an acoustic televiewer. So optical televiewer takes a 360-degree image of the inside of the borehole, and this is useful to look at the rock type, the color of the rock. It can also be used, for example, to see staining from fluid flow from like a fracture to determine the flow direction. One disadvantage of this, though, the water does need to be clean. Not crystal clear. I mean, crystal clear is perfect, but it does need to be relatively clear to see this to the side of the borehole. So acoustic televiewer, then, which uses sound waves to determine the exact shape and diameter of the inside of the well. So this is kind of a fancy caliper tool almost. So here you can see not only the fractures, but you can get an idea of how deep they are, their shape. And, as such, this and the optical tool work extremely well in tandem, right? So you can see on the right here is some borehole data. So, there is the caliper tool, which is showing the fracture there at like 66 feet or so. And then on the right, you have the optical and the acoustic log here, which is by the red arrow there. And so you can see the fracture in the optical tool, and you can see the color and the rock type. You really can't get any sense of how deep the fracture is. So the acoustic tool there, which is shown all the way on the right there, will, if you had the scale up here, will give you the actual depth and shape of the fracture. So here's just kind of what all of this data might look like. So most of it's just kind of squiggly lines, except for the acoustic and the optical televiewer. All right, next slide. And so here's an example, just kind of using all these methods to do a whole geologic framework from some boreholes. And you can see a single section of a log here on the left. So again, this is an optical televiewer log on the left with some fracture or with some veins and some bedding mapped with the red and green lines. So the arrow is pointing to one of the gray beds here, which is acting as a confining unit to the surrounding red beds. So really, just with the single well, right, you can get a good idea of the local geology, what's going on there, what the rock type is, things like that. And then, with multiple wells, you can construct the whole geologic framework of a study site. So you can see that on the right here. So in this case, the data was made with 9 wells. Monitoring well 3 is what I have shown on the left here is circled with the red dashed lines. So you can see from this, we have again, a complete framework of the site. So showing where the red beds are, where the gray beds are, the confining units, what the dip angle is, and you get an idea of, what's going on here. And again, to go further than that, right, if we can combine borehole data with the previously discussed surface methods, right, to fill in any data gaps here, you can have an even more complete picture to the whole study area. So, to summarize, again, surface and borehole geophysics are cost-effective tools for remediation sites. Surface methods are non-intrusive. They're useful for contamination, groundwater mapping, underground storage tanks, monitoring well placement, hydrogeologic frameworks can be rapidly deployed for the most part in the field to collect high-resolution data. And so this concludes that whole section of geophysics, and thanks for listening.
Thank you very much, Mike. Up next, we have Tyler Lucas and Carla Macaroni to discuss the updates to Chapter 9, Soil Gas Surveys.
Hello, my name is Tyler Lucas. I work for the NJDEP for the Bureau of Environmental Measurements and Site Assessment as an environmental specialist. I'll be talking about Chapter 9 Soil Gas Surveys with Carla. Next slide, please. This slide just details some chapters within Chapter 9 for soil gas surveys. Next slide, please. This is the rest of the chapters. There have been very minor changes since 2005, but one major change is that the Chapter 9.6 for health and safety has now been moved to Chapter 4. Next slide, please. Soil gas surveying is a screening tool used to identify and evaluate the extent of VOCs in the subsurface. It is used to assess vapors in the pore space of the soil, typically 1 to 3 feet below grade, but it can be 5 or more feet depending on where the water table is. It assesses the presence, composition, and possible sources and distribution of contaminants in the subsurface. Soil gas is not just generated from outgassing from a release. It is also generated by biological decomposition, chemical reactions, and physical decomposition. Soil gas is transported by means of molecular fusion, molecular diffusion, and convection. We in the department use the data for the location and installation of soil borings and monitoring wells. We also use the data for the design of remedial systems such as SVEs, then the monitoring of them. You can also use it to monitor release from USTs. I just want to keep in mind that it is not a substitute for the investigation and delineation of VOCs in lieu of soil borings and monitor wells. There are 2 types: active, where a volume of soil gas is collected from the vadosone into a sample container or direct reading instrument, and passive, which uses sorbent materials such as activated carbon placed within the vadosone. Vapors are then absorbed over time using the ambient flows of the vapors through the subsurface. Next slide, please. Vapor transport theory. Subsurface contamination by VOCs may produce a concentration gradient in the soil gas that decreases from the direction away from the source body or contamination. It is detected in the unsaturated vadosone when it moves upward from the saturated zone via capillary fringe. But keep in mind the source may also be present in the vadosone. Concentrations of VOCs in soil gas is a function of their concentration in groundwater, aqueous solubility, soil and subsurface characteristics, degradations, and vapor pressures. There are also vertical and horizontal concentration gradients from VOCs in the subsurface. Next slide, please. There are site-specific characteristics you got to keep in mind. This slide I'll be talking about landfills. The type of contaminant spilled and its components, along with any breakdown product, must be evaluated to determine the best compounds for detection in the vadosone that will represent the contaminant source and plume. The image on the left shows the typical concentrations of a phase 4 landfill in regards to methane, carbon dioxide, and the rest. The image on the right shows the 4 phases of a landfill. Phase 1 lasts about a year. It's aerobic, where the microbes are using up oxygen in the decomposition process. Hydrogen increases, carbon dioxide increases. Then we enter phase 2, where hydrogen starts peaking out. Oxygen is now depleted, it is anaerobic. Carbon dioxide peaks at about 60%. Phase 3 is the longest phase, where methanogenesis starts rising up. This uses hydrogen, carbon dioxide decreases a bit. And then we enter phase 4, which lasts typically about 20 years, where methane and carbon dioxide are anywhere from 40 to 60%. But landfills will produce gas for 50 plus years. Next slide, please. There are chemical and physical properties that you need to consider. One major consideration is vapor pressure, which is the pressure exerted by a vapor that is in equilibrium with its liquid phase and is a measure of the relative volatility of a contaminant. Groundwater contaminants with high vapor pressures will diffuse more readily into the soil horizons and are therefore excellent targets for soil gas analysis. Compounds that have vapor pressures higher than 1 millimeter of mercury at 20 degrees C are very good targets for soil gas analysis. These are BTEX compounds, PCE and TCE as well for chlorinateds. Vinyl chloride has a vapor pressure of about 2600, and it would be good just based on vapor pressure, but you also need to consider microbial degradation, which is the conversion of contaminants to mineralized end products through the metabolism of the microbes. The resistance of a compound to biodegradation can be a limiting factor to the applicability of a soil gas survey at a site. Degradation can reduce the amount of contaminant, especially the non-halogenated hydrocarbons, particularly C5 and higher. This limits the effectiveness of a soil gas survey where groundwater is deeper than 25 feet, shallower than 5 feet. Soil gas probes must be driven within 5 feet of the water table to obtain a reliable soil gas signal. Next slide, please. This slide I'll be talking about chlorinateds. The image on the left shows the breakdown products of the various stages of chlorinated compounds. So PCA, PCE, and TCE break down into the dichloro compounds, which breaks down to vinyl chloride, and they break down even further. You need to keep in mind that the stability of a halogenated compound is related to the number and type of halogens. Solvents that have 3 to 4 chlorines degrade more slowly, so there is little impact on their detectability in soil gas. Those compounds are PCA, TCA, PCE, and TCE. The dichloro compounds are produced as the first breakdown products of the primary chlorinated compounds, and they tend to degrade a little faster. But be aware of that vinyl chloride is monochlorinated and is a second stage degradation product, and it is the least stable chlorinated solvent in soil gas. Therefore, vinyl chloride is rarely detected in soil gas over a contaminated groundwater plume, and is an unreliable indicator of groundwater contamination. So if you're at a chlorinated site and you're detecting the parent products in the soil gas, and you're not detecting vinyl chloride or detecting it at low levels, that does not mean that vinyl chloride is not above standard in the groundwater. Next slide, please. There are also geological factors you need to be aware of. One major one is soil permeability. That is the measure at ease at which the gas moves through the sediment. It is related to the grain size and the amount of water in the soil. Clays, fine silts, and waters reduce the pore space and severely limit soil gas movement. When conducting a soil gas survey, ideally we want homogeneous soils across the site. Heterogeneous soils across the site leads to poor delineation and misinterpretation of the contaminants due to the interferences from the different soil conditions. We also have barriers and conductive zones. Barriers are obstructions that can be natural or man-made. These are asphalts, concretes, landfill caps, clay layers, perched water, frozen soil. These prevent the vertical movement of VOCs in the subsurface and traps VOCs below it. We also have conductive zones, which are areas where soil gas vapors move preferentially since the vapors are going to follow the path of least resistance. These are our natural buried former stream beds, gravel lenses, and fractures. They can also be man-made, such as the gravel bedding around utilities and pipelines. Next slide, please. We also have hydrologic and hydrogeologic properties. One major thing to consider is water table oscillations, which are changes in the depth of water table, and those can have a large impact on the vertical transport of contaminants. The movement of the contaminated water smears across the sediments, increasing the surface area of the contamination. So if anyone has done a soil boring at a gas station, they have probably seen that smear zone in the soil boring. So a significant water level increase followed by decline will have a greater effect in introducing VOCs into the vadose than other types of water table fluctuations. So it is probably not a good idea to conduct a soil gas survey after a major hurricane. We also have background water quality. So the presence of other contaminants can increase the difficulty of delineating a particular contaminant in question due to the number of dilutions required. Several plumes may also exist that partially or completely overlap from different discharges. Next slide, please. We also have rainfall, barometric pressure, and wind. Rainfall usually has a short-term effect on soil gas measurements. Even in heavy rains, if the soils are normally unsaturated, the rain shouldn't produce a saturated condition for more than an hour. The caveat to this is that soils that are high in fine silts, clays, with a shallow water table of under 6 feet, it's not recommended to do a soil gas survey at that site. Low barometric pressure and winds can increase the outgassing of soil vapors in the soil pores at the very surface of the soil, but that usually does not influence the samples collected several feet below the surface. The caveat to that is that barometric pressure changes can affect the soil venting discharge rates where an open air conduit exists. So an example for that is the passive vents on a landfill. When you have low barometric pressure, which is a barometric pressure below anything 29.8 inches of mercury, the differential pressure causes the landfill to burp, venting the landfill gases into the atmosphere. When you have high barometric pressure, which is any barometric pressure above 30.2 inches of mercury, the pressure differential forces the ambient atmospheric air into the landfill. So the idea is to collect all the samples in the shortest period of time under the same meteorological conditions. This reduces the effect of the changes, and therefore you can have a greater confidence in the correlation of results. Next slide, please.
Okay, everyone, this will be test poll number 3, which will be a true or false question. The question is grain size and the amount of water in soil can impact how soil gas moves in the subsurface. A is true and B is false. You will have about a minute to answer this question. Remember to answer the question in the poll and not in the chat. Okay, looks like everyone has answered. Next slide. The answer is true A. I will now turn it back over to the presenters.
Yeah, so one thing to keep aware of is that there is the idea of short circling. That is when a pore seal leads to the ambient atmospheric air moving down the annulus, and that leads to non-representative results. It is very important to have a good seal, so you should use clay or bentonite. Pressure measurements are also important when conducting a soil gas survey. These pressure measurements must always be made prior to obtaining a gas sample. There is a correlation between pressure measurements from soil gas wells at the various depths in regards to the atmospheric pressure oscillations. These oscillations in barometric pressure occur twice daily due to solar and lunar gravitational forces, with high pressures at 10 a.m. and 10 p.m. and low pressures at 4 a.m. and 4 p.m. So the deeper the interval, the greater the lag time for the changes in pressure. So the image on the right shows a rough relationship between the two. The brown line shows the barometric pressure. The blue line is a shallow well where it lags a little bit, but it follows the curve of the barometric pressure. The green line is the intermediate well where it lags even more, and the red line is for a deep well which lags significantly and doesn't really follow the curve. Next slide, please. This is a real-world example of the relationship, the inverse relationship between the methane discharge rate and barometric pressure at an unnamed landfill in New Jersey. The x-axis at the bottom shows the dates of sampling. The left y-axis shows the blue line shows the pounds of methane produced per hour. The right y-axis is the barometric pressure, which is the red line. And as you can see, there is an inverse relationship between barometric pressure and methane discharge. When there is low pressure, the landfill vents landfill gases like methane, and when there is high pressure, the atmospheric air prevents the landfill from producing methane, where it lowers it significantly, sometimes even preventing the production of methane. Next slide, please. So we have investigation sampling designs. So where do we place our samples? We have the grid pattern, which is this covers the whole property, and sampling points are set on perpendicular lines at equal distances along the line from each other. This covers the whole property. You'll find the sources, but you'll also find a whole lot of low levels or non-detects. Then in order to reduce the amount of samples required, you also have transect lines, which are sampling points set on parallel lines placed between the impacted area and the suspected source of contamination. You can quickly find the area of contamination, but it may require further sampling in order to pinpoint the exact source. You also have bias sampling, where sample points are placed near a suspected source of contamination to find the hotspots. You might do that at a UHOT site. You also have random sampling, which uses the grid pattern, but it uses a random number generator to designate the areas of which are targeted. That lowers the amount of samples required. And then you have combined, which you can use any of the above designs in that regard. Next slide, please. So we talked about where the samplings are, but what about the spacing? For sub 2 acre UST sites, the spacing can be anywhere from 10 to 50 feet between the samples. For larger industrial sites or landfills where it can be expected that contamination is widespread, the contamination can be anywhere from 400 to 500 feet. But you just need to keep in mind that the sample spacing should be at a minimum 2 to 3 times the depth of groundwater. And then if two sample locations have 2 to 3 orders of magnitude difference between the two in regards to concentration, you need to come back and collect samples between those 2 points. And just keep in mind, soil gas surveying is not a high resolution technique for contamination delineation. Next slide, please. So we talked about where and the spacing, but what about the frequency? That depends on the objective and the results of the soil gas survey. So for the initial screening, usually one round of sampling is required to find the potential VOC sources, with potentially a second round to further delineate and explore. But when you have a remedial system in place, a soil gas monitoring program will exist that use permanent probes at sites such as industrial sites, landfills, and UST sites, and those may be quarterly or monthly. Next slide, please. So we have the active sample collection methods. Like I said at the very beginning, an active sample collection methodology involves pulling a vapor sample through a temporary or permanent probe to the collection device or analytical device. This gives us a snapshot of the soil gas conditions at a particular time and depth, and this method allows for rapid soil gas collection and analysis from the targeted depths. Next slide, please. These are the containers in regards to active soil gas sampling. The image on the right shows a couple of them. We have gas sample bags, which are Teflon, metal coated. If you have a negative pressure in the probe, you need to use an evacuation chamber and a pump. You need to leak check those airbags as they can rip and the O-rings can wear out. Adsorption of contaminants is still possible, and it has short holding times of anywhere to under 3 hours to 24 hours, and potentially up to 3 days, depending on the method used. You have glass bulbs, which are inert but easily breakable, and adsorption and leakage is possible from the ball valves, and those have short holding times of under 24 hours. You also have syringes, which are easy to clean and replace, but there is the potential for adsorption and leakage from the plunger, and those have holding times of just minutes. And then there is also the stainless steel canisters, which are almost exclusively pre-evacuated. They are collected based on vacuum pressure. Sample lines must always be purged prior to sample collection, so you're not drawing in ambient atmospheric air. And those have holding times of anywhere from 7, 14 to 30 days, depending on the method used. Next slide, please. This is an example of some of the probes that can be used in sample collection. The first image on the left shows a slide hammer being used to drive a hole in the ground. The slide hammer is taken out. 1/4 inch stainless steel tube is placed in the hole, sealed with clay. That connects to PTFE tubing that can connect to either an airbag and an evacuation chamber and vacuum pump, or to a stainless steel canister, or to a direct reading instrument. The second image is a drive ground probe, which is driven into the ground with a slam bar. The drive cap is lifted up slightly to expose the gas inlets to the soil pore space, allowing you to draw in a sample. The third image shows a whole bunch of examples of the temporary soil gas probes. The first one on the top is a Schedule 40 half-inch slotted PVC screen that is also in permanent wells as well. The second two below that show a more handmade soil gas probe where it's using a PVC riser that is drilled with a hand drill wrapped in a nylon screen. Below that is the stainless steel drive ground probe, which is about as wide as a quarter. Below that are also expandable drive points, which can be connected to PTFE tubing. And then just below that is the quarter-inch stainless steel tubing, which you can also stick a stainless steel screw at the very bottom, place it on the soil, use a slam bar to slam it into the ground. Depending on how tight the soil is, you could maybe lift it up by hand, but you're probably going to need to use a jack. And then you can connect it to tubing, purge it, and collect the sample. The last image shows an example of something to be aware of in regards to short circuiting in a soil gas probe. Instead of the inlets drawing in air from the pore space, it's drawing in the atmospheric ambient air, and that's not something we want. Next slide, please. Here is an example of the more permanent soil gas wells. The image on the left shows the construction of a soil gas well. Soil gas wells follow the same construction requirements as a monitoring well. They're just installed above the water table. The second image shows a ball valve, which is very important because you need pressure measurements. So the ball valve can be closed. You can connect it to a manometer and tubing that's zeroed out, and then you can open the ball valve, and that way you don't have to worry about drawing in or having air come out of the probe. The third image shows an example of some of the wells that are used. You have clustered wells, which are individual wells at different depths, placed close up to each other. Then you have nested wells, which are individually screened wells, individually screened probes within one wells at different depths, divided by bentonite. You also have multi-screen wells, which is one probe in one well with multiple screens, which you need to use a packer system for. And then you have multi-port wells. Next slide, please.
Hello, everyone. I am Carla Macaroni, and I work in the Bureau of Environmental Measurements and Site Assessment, specifically in the Site Assessment Group. I will be discussing the passive soil gas sampling portion of Chapter 9. This method passively collects soil gas through sorbents utilizing diffusion and absorption. The concentration gradient is formed, pulling the vapors to the sampler. This method, as Tyler stated earlier, should not be used in place of groundwater or soil sampling, as further investigation should still be performed. Passive soil gas surveys, however, are a good screening tool. Next slide, please. The first main type of passive soil gas sampler that can be used is the AGI sampler, formerly called Goresorber. This is one of the two different samplers that you can use, the other one being Beacon, which will be discussed later. The sampler has absorbent material contained within an outer core. We have found this type of sampler to be fairly resistant to moisture in the ground, which is one of the key factors that could potentially affect your soil gas survey results. Next slide, please. Here we have an example case in which the department used the AGI samplers to help determine potential contamination on site. For this particular case, we didn't have verifying information on potential AOC locations. And here we were investigating VOC contamination, and so you will see PCE is mapped. We laid the AGIs out in a grid-like pattern to help us pinpoint where we should further do our investigation and put our boring locations for our groundwater and soil samples for further investigation. We'll often use this type of soil gas survey to help us in these types of cases. We've also found that since these samplers tend to be less invasive to install on a property owners tend to be more happy to let us on site, as this helps us to not create as many larger borings, which are often associated with geoprobe sampling. And because of that, we could tell property owners, we're going to put 30 small holes, but this will help us preventing from putting 15 to 20 large boring holes on your property. Next slide, please. So the other main type of passive soil gas sampler that can be used is the Beacon soil gas sampler, and they consist of two sets of absorbent cartridges contained within a glass vial. Some of the limitations to this type of sampler include that only 13 chlorinated VOCs were tested in the laboratory for validated uptake rates, and Graham's law of gas diffusion is used to calculate the uptake rates for other VOCs. However, all chlorinated compounds targeted by the Goresorber, which the Beacon uses, were included in the uptake rate study. For both of these samplers, you would also need to use the specific laboratory associated with each one. And for Beacon's case, it'd be Environmental's accredited laboratory. Those are the two main limitations for these two types of samplers. Next slide, please. To install either sampler, you would drill a hole with a hand drill 1 to 3 feet in depth and lower the sampler into the ground. For Beacon, aluminum foil is used when installing into asphalt or concrete. For AGI samplers, we've also found that modeling clay can be used to seal holes in concrete or asphalt. For sampling locations located in grass, we have found that the appropriate size cork can be used to seal the hole properly. Next slide, please. So again, for sample depths, we found that 1 to 3 is a recommended depth. If you tend to shoot for 18 to 24, ideally, as anything deeper could become difficult and you'd risk of hitting, utilities. More shallow installations may risk the sampler being affected by weather or another outside source such as animals. We've lost a couple samplers to some deer and dogs in the past. Generally, we like to place the samplers in a grid-like pattern, about 25 feet between them. For larger sites or suspected non-contaminated areas, spacing of 50, 75, or even up to 100 feet can be used. If you're doing larger areas, such as a residential, transect lines may be more appropriate for that type of sampling. Next slide, please. Sample exposure time. 3 to 14 days is the recommended exposure time for these types of samplers. Again, we have found that the medium range of 5 to 7 days does tend to be the best, as they're not overexposed or underexposed to any conditions on site. Multiple surveys. The use of multiple surveys may be necessary. In some cases, you may find contamination coming from another location, or missing samplers that were lost in the field could mean missing data points and may require a second survey for you to fill in those gaps. You may also find that if you're sampling multiple sites in an area, it may be beneficial to perform those surveys on the same day at the same time, if possible. Data interpolation. In interpreting the data, locations with higher concentrations can be used to help target areas for further investigation. The data can be used to delineate and help determine the extent of subsurface contamination, and thus helping you place your further boring locations with your further investigation. I would also like to quickly again discuss some positives and negatives of using passive gas soil surveys. Positives include that these samplers can be used to help determine subsurface contamination over a large area. Installation generally requires minimal tool use, and a large number of samplers can be installed in a short manner of time. We found you can install about 30 samplers in a 2-hour time period. They do tend to be less invasive to properties, and so property owners find that beneficial. Some negatives can include that, like I stated earlier, you'd have to use the individual laboratory for each sampler, and also these samplers tend to be expensive per unit. Also, the results can be inconclusive, determining on if you miss or lose sample locations or points, and so you may have to go back out and perform a second survey. However, if you're simply using it as a screening tool, a one-time survey may be sufficient. I'm going to turn it back over to Tyler. Next slide.
So analytical methodologies, you need to make sure that the method to analyze is consistent with the collection methodology and the objectives of the investigation. So sensitivity, are we talking parts per billion, parts per million, percentages? And then the selectivity, which compounds for what specific, which method for what specific compounds? So total organics 15 and 17 for volatiles, EPA 3C for landfill gases like methane, nitrogen, oxygen, and carbon dioxide, EPA 25C for non-methane organic compounds. And then obviously cost is very important. Analytical work costs a lot of money. Then we have detector tubes, which is when you use a tube to draw a volume of gas through the tube. That creates a length of stain along the tube, and depending on how long that stain is corresponds to the relative concentration of that specific compound. They're relatively inexpensive, but other gases and humidity may bias the sample. We have our direct reading instruments like flame ionization detectors, photoionization detectors, and combustible gas analyzers. You need to be aware of the limitations and sensitivities of the meter, so you need to absolutely read the user manual and technical guidance documents that the manufacturers supply. So one thing to keep in mind is that the PID uses a lamp to ionize the volatiles in the air, So the standard lamp on a PID is 10.6 electron volts. There are also 9.8 and 11.7 electron volt PID lamps. So if you're at a chlorinated site where you may expect a compound like TCA, which is tetrachloroethane, and 1,2-DCA, those compounds have ionization potentials above 11. So the standard lamped PID is not going to read those compounds. So you would either have to use the 11.7 EV lamp, or you would have to use a flame ionization detector, which uses hydrogen to produce a flame. And the FID has an ionization potential of about 15.4. And then one thing to keep aware in regards to the flame ionization detector, in order for that flame to exist, there has to be 16% oxygen at least. So if you stick it on a well that has less than 16% oxygen, the FID is going to flame out and you're not going to get a reading. Now, if you want to determine the actual compound specifically in the field in regards to the soil gas, you can use a portable GC. One of the problems with the portable GC is that it is expensive to own, expensive to rent, and it requires a lot more training and consideration than just using a direct reading instrument. And then obviously if you're collecting it in a sample collection device, you're going to send it to a certified lab and they're going to run the samples under a GCMS. Next slide, please. I just want to say in regards to soil gas data interpretation, soil gas measurements just approximate the contaminants of interest in the subsurface. There are site and compound specific considerations when interpreting that soil gas data. Again, as I said at the very beginning, VOCs can be altered or eliminated by biological or chemical transformations. So again, TCE gets dehalogenated into the dichloro compounds and then eventually into vinyl chloride, which breaks down even more. And also there is the reduction of organic hydrocarbons to methane and carbon dioxide by oxidation. Soil gas data is not a one-to-one relationship match with the groundwater contours. And be acutely aware of volume per volume, which is parts per million and parts per billion, and mass per volume, which is micrograms per liter or milligrams per meter cube. If you get results from a lab, they're going to give you both, but you don't want to confuse them. And you can also convert them between the two. You just need to know a constant based on standard pressure and temperature and the molecular weight of the compound in question. Next slide.
Okay, thank you very much, Tyler and Carla. We will now begin our first question segment. Our first question came in during Chapter 5. This is an IDW question. Do you need any permits to treat groundwater with an activated carbon on your sites prior to discharge on ground?
As far as I know, there is there is no necessary permit needed to do that. Should be covered by the permit by rule.
Okay, the second question comes in. This audience member wants to know the difference between type 1 and type 2 deionized waters.
I personally don't know the answer to that question.
I can answer that question. So I brought up that change during the chapter 5. I brought up that topic during chapter 5 where previously the manual stated ASTM type 2 water, but now ASTM type 1 or type 2. So the ASTM has certain requirements for the different types of pure water, like laboratory or reagent water. So type 1 actually has more stringent requirements than type 2. The reason that this came up as a topic to be changed is because even from my own experience in some years ago, because the field sampling procedures manual specified type 2, some manufacturers by standard would use type 1, but because the manual said type 2, some people would ask special request type 2 just to meet the criteria of the manual. But in reality, type 1 is ultra pure. It goes through additional steps and there's different resistivity, sodium, chloride, etc. standards for each of these different types. So I just brought that up because it is some of the manufacturers' standard. They use type 1, so we just provided clarification that type 1 is fine. You don't have to go and find type 2 water for your PDBs.
Okay, our next question comes in during Chapter 6. How does the first two samples require for volume average purge apply to wells with longer prior sampling history prior to issuance of this guidance?
If I understood the question correctly, I believe the answer would be if you haven't done volume average sampling in the past, we would like you to do it kind of at your next opportunity.
Okay, and the next question is,
Kyle, hold
sorry.
on. I'm just going to jump in from the permit perspective on that question, since that's probably what a lot of people are thinking about with that question. My name is Alyssa Ambacher. I'm with the Bureau of Remedial Action Permitting. And as far as the volume average purge sampling goes, like we know there are a lot of sites that predate the Field Sampling Procedures Manual, but like Greg said, we do expect to see that volume average purge sampling happen at the site. If you haven't done it, you should definitely justify in whatever document you're submitting why you didn't. You can deviate from guidance, including the Field Sampling Procedures Manual. And if you choose to deviate from guidance, then you definitely need to justify, and you should let us know that your method is equally protective, and you should let us know of any site-specific circumstances that are preventing you from doing that type of sampling. So sometimes that could be like a low yielding well, or if you're sampling for turbidity sensitive compounds. So there are reasons that we would accept to not do that, but make sure as guidance comes out and is updated, you are applying that guidance to your site, even if your site predates that guidance. And then for well closeouts, we do recommend the volume average purge sample. Thanks.
Okay, our next question is, water quality indicator parameters are only required for the first 2 rounds of sampling and not the others?
At this point, yes, with the exception being if you're doing low flow sampling, you need to do them because that's critical to the method. But if you continue to do volume average sampling past your second round, they are not necessarily needed. It's not mandated for that method anymore.
Okay, and our next question comes in during the soil gas surveys. On active soil gas grids, can we get elaboration on sample spacing with regard to depth to water?
Yeah, so again, it depends on how deep groundwater is. It needs to be driven at least 5 feet above depth to water, and that helps you get a gas signal.
Okay, here's another question. Does the Field Sampling Procedures Manual, VI guidance, address influence of induced pressure gradients? For example, air discharges within a building, fume hoods, fry grill hoods, building HVAC systems, etc. Where these situations exist, is the selection of sampling points left to the LSRP?
Could you repeat that?
Yeah. The first part of the question is, does the Field Sampling Procedures Manual, VI guidance, address influence of induced pressure gradients, such as fume hoods, fry grill hoods, and HVAC systems?
Do you want to answer that, Carl, or do you want me?
I don't have a definitive answer for that one, Tyler, if you want to take it, or I see Carrie's hopped on as well.
The
Okay.
short answer to that question may be that the section that was just covered in the manual does not cover the indoor air vapor intrusion. So we can take that question and take it back to folks who could answer it and then send you an update via email. Because the section that Tyler and Carla covered was very specific to soil gas surveys.
Okay. We will get back to the answer at a later date. Moving on to the next question. Does purged water field treated through carbon require lab analysis to confirm it is clean prior to discharging to ground?
I would say that they certainly have the option to do that, but they should know roughly the water quality of the data that they're thinking about purging to ground and looking at, I guess you call it like flow through times, like how much carbon they need to use, what depth of carbon they want to run the water through to try to remove as much contamination as possible.
Yeah, can you please elaborate on what volume average sampling is and how to do it, and where to find the details on it?
Volume average sampling is basically the original sampling in the environmental field. It goes back to the 80s, and for people like me that have been involved in this for 36 to 38 years, back in the 80s, that's all there was. Everybody sampled by volume averaged, where you purge 3 to 5 well volumes before you collect your sample. That was the standardized method back then. There's a lot of guidance on how to do it in ITRC, EPA. Our manual does go into a fair amount of detail. It has its own section in our manual.
Okay, the next question is vertical profiling not required for volume average sampling?
No, it's not, because volume average sampling purges the most water out of the well. So the intent is that if you are purging the well at a rate that is close to the well yield, which we like people to try to accomplish, you should be pulling water in pretty much across the entire well intake interval. So your sample represents a larger area of what can get into the well. So we're taking the position that if you're sampling by volume averaged, you do not need to vertically profile.
Okay, for a groundwater vertical profile, what are the appropriate depths and how many data points?
That is discussed in the section on vertical profiling in the manual. It can be kind of site specific. There's a whole section there's a whole subsection in that section that talks about all the criteria that one should evaluate when trying to determine where to collect the sample, and the general guidance is one sample roughly every 5 feet, but that where you sample in that 5 feet can be affected by the type of contamination, the surrounding geology, what was found in the past. So you need to sit down and think about where you're going to sample and why before you go out and do it. And like I said, we want people to turn in the depths that the sample was collected and an explanation of why those samples were chosen when they turn in their results.
Okay, when we have a site where volume average purge results in lower concentrations than the multi-level passive sampling does, would we still need to do 2 rounds using volume average purge to close the site?
Okay, can you read that again? It sounds like they started off with volume average.
When we have a site where volume average purge results in lower concentrations than the multi-level passive sampling does, would we still need to do 2 rounds of volume average purge to close the site?
That sounds like that might be a policy discussion that it sounds like what they found kind of goes against what we're recommending. So I don't think we would want someone to justify closing out a well or a site if it still had an exceedance of the groundwater quality. But they could certainly, submit that question to the department for greater discussion.
Okay, next question. With low to no flow into wells in bedrock, is a grab sample collected within the well space via a double-sided bailer valid for VOC analysis?
As I mentioned before, sampling for wells that are very low yield is always tricky. I'm not too sure there is a perfect method to do it, and that's why I kind of mentioned that you might have to try to take samples via a couple different methods to compare the results to see which particular method works out better. It has to do with the retention time of the water in the well, which is related to how fast the water is flowing through the well, versus if it's a very low yielding well, any type of purging is going to cause a potential problem with drawdown. And that's why we're recommending they try a couple different things and just see what works out best.
Okay. When do you have to do volume average sampling?
At this point, the way the manual is set up, it's pretty much just at the beginning and at the end.
Okay. Is vertical profiling required in a bedrock well that has a significant vertical flow component?
I think if they've already documented that you have vertical flow, they might be able to make a technical justification that vertical profiling might not be appropriate, because chances are you're just going to get the same results. But again, they would have to supply the documentation as to how they determined that there was vertical movement in the well, provide information on, maybe where they took those measurements to prove to the agency that they have that issue.
Okay, looks like this will probably be a last question. Can you close out wells at your site using low flow rather than volume average purge if you have low-yield wells which have significant drawdown when purging 3 to 5 well volumes?
Potentially, yes. That goes back to that discussion I had about low yielding wells. There's no good way to sample them. Every method has its drawdown, and that if they do an episode where they collect multiple samples and they say, low flow or passive gave the highest number, they could potentially argue that that would be the appropriate method to close the well out, given what we found previously.
Okay, that is all the questions we have for now. Next slide, please. We will take a break. Also, quick notice, if your questions are not answered during this training, the department will get back to you at a later date with an answer. Thank you. And we will reconvene from the break back at 12 o'clock. Thank you.
Hello, it is 12 o'clock. Hopefully everyone is back from their break. We're going to get started with the next presentation. Now it is Lee Lippincott presenting Chapter 10, Documentation.
Thank you, Taylor. Hello, I'm Lee Lippincott. I'm with the Division of Science and Research Bureau of Risk Assessment, and we're going to discuss Chapter 10 on documentation. Next slide, please. These are the individuals that contributed to the updates and responded to comments on Chapter 10 through 13. These chapters were posted for use on December 2023. Next slide, please. These are the subsections in Chapter 10 that we're going to discuss. A brief introduction, which talks about the importance of documentation for the remedial strategy, field data sheets and logs, field notes, both of which are different from each other and have different purposes. A section on documenting sampling locations and photo documentation, and the current state of sample collection paperwork, sample labels, chain of custodies, and sample analysis requests. Next slide, please. This chapter was updated to include all the current information that was present in the chapter. It also was updated to account for the submission of digital field notes and photographs, which we'll talk about later in the presentation, and the sample collection section as well was updated. Next slide. Appropriate field documentation, field notes, field logs, photo documents. Photo logs are an important part of your field investigation process. It is critical as a basis for the technical conclusions drawn from the data that will influence and justify the remedial action selection. Documentation should be maintained from cradle to grave, because you're the individuals and professionals with boots on the ground at that particular site. So it's your responsibility to document the progress and remedial activities and to trace the possession of and chain of custody of samples collected from the time of collection through the analysis and final disposition. Chapter 10 contains the details about these proper documentation. Next slide, please. Field notes are descriptive, which means describing or classifying your qualitative and quantitative observations in an objective and non-judgmental way. They're reflective, using your experience to relate the importance of an observation to the remedial goals. They're analytical. They're specific quantitative field measurements that you're making that provide a critical information about the remedial activities and their effectiveness. And versatile. These are observations that you use from your experience that have the potential to be adapted and to improve the remedial activities. Next slide. Although the field notes are not required to be submitted to the DEP or other regulatory agency, they should contain contact information and site-specific information, which should be available upon request. If the field notebook is dedicated to the site and is used by several individuals, the contact individual should be identified for each entry in the field notes. Pagination is important. It ensures that the notebook is not missing any particular information. Next slide. Dates and times are important when documenting water quality parameters like temperature and dissolved oxygen, which are on a diurnal cycle. Field instrument like PIDs give an indication of exposure to hazardous conditions throughout the site. So locations that are analyzed must be documented in order to reduce the exposure of the field staff. Next slide. Specific sample location information, such as the description of the location, the depth of the sample taken, tide conditions, soil conditions, water color, or any other condition that can be noted should be included in the field notes. In addition, you should also document out of the ordinary events, such as equipment failure, damage to monitoring wells, or evidence of tampering in those wells, and observations of gross contaminations like odors or specific areas where gross contamination can be observed. Information that the field staff believes may be useful or pertinent at a later date. Next slide, please. There are several reasons for taking field notes. These include providing a record of the conditions of the site at a specific time, such as during an inspection, documenting specific activities that occurred at the site, and noting information in the field for its use, such as recording low-flow well field parameters for comparison purposes to determine stabilization. And we'll give you an example of that on one of the field notation examples that we have presented later on in the discussion. Several additional reasons for, next slide, I'm sorry. Several additional reasons for taking field notes is that the notes allow for the recreation of an event. Documentation allows the review of site activities, and documenting specifics about the date, time, place, and purpose of a particular site visit are important for maintaining the timeline of events that have occurred. For EPA lead sites and state lead technical guidance, there's a wealth of information about field note documentation. We've provided you with one link here to the information that are available from the EPA. Both written and electronic field notes are acceptable. Notes are taken prior to the completion of any field log sheets, and the log sheets, the number and type of log sheet should be documented in the field notes. The field log sheets are required, and these must be submitted in PDF format to the department or the regulatory agency. Field notes should also be available for review upon request. Next slide, please. Here's a generic example of the contents in field notes documenting the recording of field parameters for comparison purposes to determine stabilization. The pages are consecutively numbered. Monitoring well identification information is consistent and uniform throughout. The tables of groundwater quality parameters are the same throughout this event, and the date and times are clearly noted. Next slide, please. This is an example of an electronic version of the field notes. The figures on the left side shows the location of the sub-basement sampling points. In addition, the exterior location of removed and abandoned underground storage tanks are illustrated. Pictures of the street level are also included for reference and scale of the figure. Scanned field notes in the center of the slide are included, and the figure on the right shows the drain locations at a specific sub-basement. The blue rectangles obscure the site-specific locations for this presentation. Next slide.
Hello, it's time for our fourth and final poll question for this training. Poll question number 4 will launch. Make sure you answer the question in the window. Field notes should include A, weather conditions, B, sample event date and time, C, names of personnel present, or D, all of the above. The poll window should be up. Make sure you answer the question. If you're seeking CECs for today's training, we will give you about a minute. Okay, next slide. The answer is D, all of the above. Back to Lee.
Okay, thank you, Taylor. In the previous section, we talked about field notes. In this part of the presentation, we're going to describe the difference between the notes and the field logs. Okay, so field logs contain specific quantitative measurement information for the department's programs to consider. Logs contain information for approval of remedial strategy for the site. You also identify information gaps, which delays the regulatory decisions that have to be made. Logs document the current condition of the contaminant source or sources. Next slide. Field logs are important because good documentation is critical for the purpose of both providing legal and defensible record of the field program and to maintain and transmit data for future assessment and interpretation. One of the definitions that I identified were field logs are the primary legal record and source of documentation for the site activities. They record summaries of all critical field activities and measurements so that the average person can understand the chain of actions, the events, and the decisions that were made. Next slide. Some field activity have specific forms for taking notes, or specific projects may require specialized forms to assist in the data organization for the site. At the end of the day, the total number of forms used during that day's activities must be indicated in the field notes. Next slide. Chapter 6 has several examples of the field data sheets and logs. They include daily calibration sheet for field analysis, low flow groundwater sampling log, monitoring well information in support of pump intake depth placement, volume average sampling field sheet, checklist for submission sampling data for the passive bag diffusion samplers, which were identified and discussed in previous slides in this particular presentation. The completed field data sheets and logs should be provided to the DEP or other regulatory agency during each document submittal. The example data sheets and logs provided in the chapter are not required to be used. However, the specific information requested should be recorded. Next slide. Here's an example of a sampling log form from Chapter 6 in the Field Samplings Procedure Manual. Going from top to bottom, we see that the top section contains the site information. The next section down contains well-specific information. The section below that has the well purge information. Below that is the sampling information. And at the bottom section, sampling log describes the depth, purge rate, and water quality parameters that document the stabilization measurements and confirm stabilization criteria, which is shown at the bottom of each measurement column. The bottom, of course, has a section for any additional information that would be relative for this particular sample campaign. Next slide. This chapter was revised to include a wealth of information for specific CSRR investigations that are linked in the text of the Chapter 10. These links provide guidance regarding the technical documentation requirements for information like soil investigation and the preparation of quality assurance project plans. This access to the online log sheets ensures that specific information that the department needs to make regulatory decisions are present in the entry items contained in the field log for that particular type of activity. Next slide. Documenting sampling locations has gotten much easier when utilizing modern survey-grade global positioning systems, or GPSs. The new GPSs have centimeter accuracy with automatic signal correction that allow for sample location, notes, and photographic capability in one unit to link all the field information into one file. If GPS is not available, then you can go old school and select a fixed reference point at a stationary location. Then using a compass readings, measuring tape, document the direction and distance vector from that point. There are several available geographical information system guidance documents, and this link is provided on the department website that you see at the bottom of the slide. Next slide, please. The following slides are an added section in the updated Chapter 10 in the Field Sampling Procedure Manual that speak to the photo documentation associated with remedial investigations. Each photograph should have recorded records of the date, the time, the person who took the photograph, the site name, the general direction and description of the site, including the GPS coordinates if collected, and important characteristics noted, and photographs such as product, groundwater, bedrock, or vegetation that's present at that particular site. The next slide will show an example form that is associated with photo documentation. Next slide, please. Here's a picture of one of the sets or elevation table locations at a dredge spoils deposition estuary site in the state. The PVC pipes on the left-hand photograph define the study area where scientists evaluate the vegetation recovery of an ecologically stressed area. The application of a layer of dredged material elevates the level of the estuary to address sea level rise. The form, which accompanies the photo or photos, is shown on the right-hand side here. This form is filled out at each picture taken at the site, and each time the location is resampled to document whether the vegetation has recovered and flourished during the resampling interval. These locations are monitored over a 5-year period, so it's critical that the documentation be consistent with time. Next slide, please. This next section was updated to address the current documentation of the sample collection process at the site. Here are a variety of different logs, seals, forms, and labels that are part of the sample collection, preservation, storage, shipment, and relinquishing process. Some are related to the legal transit of environmental samples. Some are required to document the identity of the field sample, which method is used, which parameter is a remediation driver, who relinquished and received the sample, and was the sample accepted by the laboratory. You get the message about the cradle-to-grave documentation for sample collection and shipment. Next slide, please. It's critical that field sample number be unique to that sample being collected, because a sample may only be one of a number of samples processed in a batch by the laboratory. This field information is transcribed into the Laboratory Information System, or LIMS, and a unique laboratory number is assigned for its subsequent sample analysis. Sample preservation specifics, method of analysis, holding times for a specific analytical parameter, and method must be specified in the Quality Assurance Project Plan and the sampling plan. The sample labels and associated documentation can be completed prior to the day's sampling event to minimize the amount of documentation that needs to be recorded in the field. Chain of custody and analytical request forms can also be partially completed so that the sample collection sequence can be planned in advance to maximize the collection effort and minimize the time that the collected samples are exposed to the environmental conditions present at the site. Next slide, please. The facility name's been removed, including the academic institution that's conducting this research for one of my treatment projects. Preprinting the sample labels and any other documentation associated with the sample, for instance, filling out as much as possible on the analytical request forms, allows the sampler to focus on collection rather than filling out repetitive information at the time of sampling. It also helps to reduce inconsistencies associated with sample number, such as the ones illustrated here. MW1 or MW-1 or MW-01 or MW space 1 could potentially duplicate analysis and costs, or lose the unique sample identification, or assign the sample to another location source. It's critical that all these numbers and all the sample labeling convention is consistent throughout the sampling collection process. Next slide, please. On the left is an example of the NJDEP sample chain of custody form that appears in Chapter 10. Many certified labs that accept environmental samples from contaminated sites have their own sample collection procedures that are consistent with the analytical method requirements. Many laboratories even have their own COC forms as well. Notice the top section of the left-hand NJDEP chain of custody. That laboratory information, time and date of and the sample container that was sealed, laboratory seal number, person preparing the samples for shipment, specific NJDEP division, bureau, and phone number and job number are listed in the next section. The analytical request section is below with a number of columns with the collected information which corresponds to the sample label for each sample. The analysis parameter, method identification column, any preservation that was used, container volume, and sample matrix. In this case, it's water. Contact information, task identifier, and report format are important as well. For instance, is the screening report adequate, or is a full-blown regulatory compliance format needed to fulfill the requirements for court defensible data? On the right side is a sample analytical request form from the New Jersey Department of Health Environmental Laboratory. When I was conducting statewide groundwater source investigation, my colleague and I had to fill out one of these forms for each public water well sampled prior to submission to the health laboratory. As you can see, there's quite a lot of information to be entered on each form, which should be filled out in advance of the sampling event. This concludes my presentation for the updates and content of Chapter 10 in the New Jersey Field Sampling Procedures Manual. Thank you very much for your attention.
Thank you very much, Lee. Up next, we have Crystal Paruzik to discuss Chapter 11, Sample Shipment.
Hello, thank you, Lee. My name is Crystal Prozik from the Bureau of Site Management, and I will be going over the updates to Chapter 11. Next slide. Chapter 11 is Sample Shipment. Here is a list of the sections from the chapter. Next slide. Chapter 11 focuses on packaging, labeling, placarding, and shipment requirements for samples collected from hazardous materials and hazardous waste. This chapter is different from Chapter 2, which also does a little bit of shipment information. Next slide. There was not too many large updates to this chapter. We mostly updated the web links, all the reference documents. We added some clarification on sample shipment done by commercial laboratories. We also made the clarification between non-hazardous sample shipment, which was Chapter 2, versus hazardous sample shipment, which is in Chapter 11. And we clarified the definition of dangerous goods versus hazardous materials and provided specific references for both. Next slide. It was a quick update for that chapter.
Thank you, Crystal. Next, we have James McCullough presenting on Chapter 12, Radiological Assessment.
Good afternoon. My name is James McCullough, and I supervise the Radiological and Environmental Assessment section at DEP Bureau of Environmental Radiation. I'll be reviewing Chapter 12 on radiological assessment. Next slide. This is an outline of the current guidance. There were some additions and reorganization, which we'll summarize in the following slides. Next. Chapter 12 provides guidance on conducting and documenting radiological surveys and sampling episodes for demonstrating compliance with New Jersey Administrative Code 728-12, remediation standards for radioactive materials. It includes specific references to the Multi-Agency Radiation Survey and Site Investigation Manual, MARSAM, which along with the Field Sampling Procedures Manual is referenced in this Chapter 12 regulations. For your information, the MARSAM Working Group is an ongoing collaborative effort to bring consistency to the methods and processes used to demonstrate compliance with federal and state radiation regulations. Work group members represent 4 federal entities that have the primary responsibility for managing radioactive materials: Department of Defense, Department of Energy, Environmental Protection Agency, and Nuclear Regulatory Commission. Its review and revision includes extensive stakeholder review and involvement, including opportunity for public input. And revision 2 is currently underway, after which New Jersey DEP may reopen this revision to this subchapter, or this chapter of the Field Sampling Procedures Manual. Next. This chapter previously only referenced naturally occurring and accelerator-produced radioactive materials, as these were historically within New Jersey jurisdiction. On September 30th, 2009, the U.S. Nuclear Regulatory Commission and New Jersey signed an agreement authorizing the state to license and regulate byproduct, source, and certain special nuclear radioactive materials. Therefore, the scope and applicability of 7:28-12 was expanded. This is reflected in the Field Sampling Procedures Manual, mainly through the addition of definitions of radioactive material types in the glossary, since we assess these additional radioactive materials with these same methodologies. Next. Section 12.4, titled Oversight, discusses relevant sections of the administrative requirement for remediation of contaminated sites, licensed site remediation professional oversight, and submission of work plans and reports to the department. This has been a common question from LSRPs managing radiological cases, so we hope this section provides more improved guidance on this topic. The Bureau of Environmental Radiation contact, website, and relevant references were also included. Next. Text throughout the document was revised to provide clearer and updated guidance and references for investigators. In section 12.8.1, titled Determination of Lateral and Vertical Extent, there is an expanded discussion of core scanning and sampling, including incorporating US NRC guidance that core soils of no more than 1 meter are composited into a representative sample if a more elevated interval is not identified for sampling. There's also reference to a new data miner report, which was developed to provide a comprehensive list of certified laboratories, parameters, matrices, and analytical methods for radiological assessment. And the instructions there point into that report. Next. The new figure 12.2 shows an example of a random start triangular grid measurement pattern, which is the preferred pattern for radiological cases, and was included to demonstrate the distinction between 2 different DCGL EMCs referenced in guidance. DCGL, Derived Concentration Guideline Level, is a derived radionuclide-specific activity concentration within a survey unit corresponding to the release criterion, which is a regulatory limit expressed in dose or risk. Elevated measurement comparison, EMC, is an assessment of elevated results which exceed the survey unit-wide DCGL. So a DCGL EMC is an area-specific DCGL. Next. The a priori DCGL EMC is denoted by the blue area, is determined during survey planning based on the hypothetical maximum hotspot area between systematic sample or measurement locations. An a posteriori DCGL EMC is denoted in red, determined when an elevated measurement above the DCGL for the whole survey unit is detected. And these two different elevated measurement areas have been misunderstood in the past. As you can see, if the yellow sample location were an exceedance using only neighboring systematic sample locations, the area affected might be 6 times larger than assumed for the a priori DCGL EMC. An example follows using these areas. Next. So using the example figure, we will assume the radium-226 DCGL is 7 picocuries per gram and can calculate the area between planned systematic grid locations is 125 meters squared. Using a table of outdoor area factors, we can determine the a priori DCGL EMC. The blue area based on the blue area on the previous slide is 18.9 picocuries per gram. This is the threshold of a field scanning instrumentation, calculated MDC, minimum detectable concentration, which would need to be achieved for the given sample density plotted. This step is completed in the planning phase before a survey is completed. Next. Now we have implemented a final status survey and identified the results of one systematic sample representing an elevated measurement location or hotspot. This area is represented on the figure by the red area representing 750 meters squared. So here we calculated the a posteriori DCGL EMC, which is essentially how elevated can a hotspot of a given size be and still be compliant by itself. If the elevated measurement comparison, if the elevated result exceeds this DCGL EMC, the hotspot fails without further review. Next. And here's an example figure showing a gamma walkover survey along with systematic sample locations on a triangular grid. So in the key, you can see the gamma walkover survey data, the count rates as counts per minute, CPM, range from the low end in green to higher count rates in dark blue. If we found this, and we selected a bias sample within that dark blue area, if we found this bias sample to be an elevated measurement location, you can see how walkover data and surrounding sample locations may help to bound a hotspot discovered in surface soils. You would also consider adding bias samples to bound the hotspot with analytical data points closer than the nearest systematic sample locations. And because it's in the corner of a survey unit, you may have to look to neighboring survey units for nearby samples as well. Next. Finally, if you have established that a hotspot complied with this elevated measurement comparison and the survey unit passed a recommended statistical test, then the final step for a survey unit is to account for the combined dose contributions from the survey unit and the hotspot. Here, the DCGL-W, which is for the whole survey unit, is the applicable, the DCGL-W is the applicable release criteria for the whole survey unit. There is more extensive discussion of this assessment in MARSIM Chapter 8. Next. This slide is just to demonstrate that it is necessary to define additional factors if, as in this example, you have multiple contaminants and multiple hotspots in a single survey unit. Next. And to close out discussion on Chapter 12, there are future developments anticipated in guidance for radiological assessment, and I have noted a few items here. As previously referenced, MARSIM Working Group has been developing a revision 2 to that guidance, And the U.S. Nuclear Regulatory Commission has also been working on additional guidance, particularly on subsurface impacts. Thank you for your attention, and this concludes what we've prepared for Chapter 12.
Okay, thank you very much, James. We are now moving on to Omar Minix, who will discuss Chapter 13, Personal Protection.
Omar, for 1 second, I just want to tell everybody that they can start putting in their questions now. They don't have to wait until the question period to put their questions into the question box. Thank you, Omar. You can begin.
Hi, my name is Omar Minix. I'm a senior project engineer with EWMA. I'm a professional engineer in LSRP. I will be discussing today Chapter 13, Personnel Protection. Can I have the next slide? And so for Chapter 13, there's a new format in this Field Sampling Procedures Manual. It's been rearranged by adding project planning to section 13.2. Respiratory protection has been moved to section 13.5. And section 13.7, which is personal contamination reduction considerations, has been added from the old section 14. And there is no section 14 in this version of the manual. Next slide, please. And so for adequate protection, prevention of contaminant exposure to workers at hazardous waste sites in all phases of investigation, personal protective equipment should be utilized as required by a site-specific health and safety plan, and personnel contaminant reduction practices must be implemented. Chapter 13 details PPE, personal protective equipment, physiological factors for use of PPE in health and safety, and personal contamination reduction that should be considered while on site. Next slide, please. So most of the health and safety is with OSHA. So the new Field Sampling Procedures Manual has links to the OSHA website, specifically 29 CFR 1910 Occupational Safety and Health Standards. There are also links to DEP Technical Guidance webpage and the appropriate DEP guidance documents such as the Quality Assurance Project Plan. There's a link for that guidance because project planning has been added for health and safety. During the time you're putting together your QAP, health and safety should be taken into consideration, and a site-specific health and safety plan should be produced for the site. And like the QAP, it should be updated for each investigation. The HAS will contain similar information as the QAP, and any work plan information like chain of command, supervisors, health and safety supervisors. It's similar to section 6.1.6, assuring health and safety of this Field Sampling Procedures Manual, and 29 CFR 1910.120, hazardous waste operations and emergency response in the OSHA regulations. There's also detailed information on donning and doffing PPE with example diagrams, and then there's the investigation-derived waste plan. An IDW, investigation-derived waste, is any waste generated during investigation or remediation activities. Examples of IDW include purge water from monitoring well development, drill cuttings, decon water, PPE, and disposable sampling equipment. The IDW plan details how the waste is generated. Is it hazardous and non-hazardous? How will it be managed once generated? The sampling, labeling, or storage requirements. Is waste disposal included in the budget? And your record training requirements for handling IDW, waste location, and time frame for waste storage for disposal. A link is provided to get more information from the US EPA website. Based on the information in that link, if you don't want to produce a separate IDW plan, it can be included as part of your QAP or work plan sampling plan. And again, there are links to the OSHA website and OSHA citations throughout Chapter 13 to get more information from. Next slide. And so here's an example of one of the diagrams from section 13.7, personal contamination reduction considerations. It shows the process from getting from an exclusion zone at a site to a support zone for level B protection. This section has diagrams for the other levels of protection as well for your own research. So in closing, the updates to Chapter 13 involve more planning by detailing project planning, respiratory planning, and an IDW plan. It has more training with citations for the OSHA respiratory training standard and more links to the OSHA website so as they update information that this guidance document does not have to go through review again. And so that is my presentation on Chapter 13.
Thank you, Omar. Now we're going to enter our second and final question session. And just a reminder that any questions that were not answered during today's training will be answered via email in the next several weeks. So for our first question, we're going to go back to volume average purge. So doesn't the hydraulic stress induced by volume average purging have the potential to spread contamination?
I don't think so. I mean, we're pulling water out of the well. The more water you pull out of the well, if anything, you're going to pull something to the well. If that's what they're really thinking about, that we could be pulling contamination to the well, that certainly is possible. But the state regulates the entire groundwater, and wells are not always, perfectly placed in the geometry of the plume. So it's not unusual for groundwater several feet away from the well to potentially be more contaminated than the water in the well, and that's one reason why we have a recommendation for volume average sampling, is that it kind of gives you a bigger footprint of the groundwater when you sample. But yes, with continued pumping, you could move some contamination from a couple feet away from the well to the well.
Okay. And the next question, when you do volume average sampling, is this for any contaminated site?
Yes. Well, I'll caveat that I did mention that if they're only sampling for turbidity sensitive compounds like PAHs and metals and stuff like that, it does allow them to not have to do the volume average method, but it's only for the sampling of the turbidity sensitive compounds.
Okay. All right, we have a question on field notes now. Do field notes need to be on paper? Can boring logs be live scribed in the field digitally?
I can answer it, Philly. Yes, so the idea is that field notes are your own personal notes that are not required to be submitted with each document submittal. So you are able to do paper notes or digital notes. If the department does request the field notes, though, they should be submitted. The field logs, however, are required to be submitted with each document submittal.
Okay. This is a question on Chapter 12. For Chapter 12, how should multiple adjoining hotspots be addressed in the EMC evaluation? Should the activities be averaged over the entire hotspot area?
That's really very site specific to how you might handle hotspots that are contiguous or adjacent to each other. So I would just recommend reaching out to our bureau for consultation if you have a situation like that.
Okay, we have another volume average purge question. Isn't volume average purge an issue for collecting volatile organic compounds due to added water agitation?
If it's done properly, there shouldn't be that much agitation. And a lot of the language that we talk about, minimizing drawdown, monitoring temperature of the pump, I mean, we are recommending procedures to try to minimize agitation of the water. I agree with the reader that you do not want to agitate the water when you're sampling for volatile organic compounds.
Okay. Define site closeout for projects with remedial action permits. Is it prior to filing for the RAP or at RAP closure?
I'm just going to jump in here for this one since I'm in BRAP. So when you are closing out, if you're going to terminate a permit, if you already have a remedial action permit, you would need to sample your wells, and they need to be below the groundwater quality standards in order to close out that permit. So If there's a permit involved, you have to sample. I don't know if there's, oh, I just lost the question. It just went away.
You want me
I
to repeat
think
it?
that's, yeah, if you could just repeat. I think that's what they were asking.
Right. The language that I was mentioning is just in a very general, broad paintbrush approach that when they're trying to close out an AOC, they're saying, this well is no longer needed because the contamination's gone. We would prefer that they do a volume average sample at that point to help prove that there's not only is the well clean, but the part of the aquifer, within several feet of the well is also clean. That's independent than the RAP issue.
To obtain a RAP, I'll jump in here as well, just to cover what Melissa what might be getting at also is to obtain a RAP, you're showing contamination. So you want to show delineation, you want to show that you have clean points to finding your plume, but we're talking about case closeout, that's the end. When you terminate the permit.
Okay, we have another volume average purge question. For volume average purge sampling for low yielding consolidated wells, rock wells, is it acceptable to calculate the 3 to 5 volume to purge from only the open hole or screen zone of the well?
It depends on your water level. And that's why I kind of went into two different scenarios that if the water table in your well, even if you're in bedrock, if the water table in your well is in the open borehole or the screened interval within the rock, that would be your calculation. But frequently rock wells are deeper than overburden wells. So it's common for the water table to be up in the casing of the well, way above the screen. So the initial calculation would be based on the total vertical column of water in the well. We do allow a situation, and I mentioned it briefly, that if they want to purge the well to the point where they're bringing the water table down to the top of, in this case, the top of the screen or the open borehole interval, they can recalculate to determine how much water they've taken out. And it's really, we're just targeting 3 to 5 well volumes of basically the bedrock section of the well, the open borehole or the screen section in the bedrock.
Okay. And another question. The December 2023 Hot Topics training addresses initial sampling, 8 rounds of sampling to establish M&A and closeout. It does not address biennial sampling requirements. Do they require volume purge similar to closeout? Is this PRCR choice?
It's what you put in your field in your sample in your monitoring plan. What you do during the duration of your permit is what you put in your monitoring plan. You want to expand, Alyssa?
Well, I was just going to say, and I think also, to close out, we do look for the volume average purge. Like I said before, we want to see that at the beginning and at the end. And if for some reason you can't do volume average purge, you need to justify why. So you can't just not do it and then not tell us why. If you're ever deviating or varying from guidance or rules, you have to justify with technical reasons in your document.
We hope that answers that.
Okay, another volume average purge question. Volume average purge on low yielding unconsolidated wells. Is okay to reason only to purge 1 to 2 purge volumes due to low well yield when purging at less than 0.5 GPM?
This goes back to the issue that I talked about, that a lot of our wells are low yielding, although it sounded like at the purge rate that you mentioned, they would be above the low yielding well criteria of 100 milliliters per minute. That's why I did stress that it's important to know the recharge capability of your well, especially in these low recharge rates, so that they can appropriate enough time, bring an appropriate pump to the well that can basically run at lower rates for an extended period of time without heating up. If they're going to do volume average, we do prefer them to try to meet the criteria of a minimum of 3. Obviously, if they bring a pump that only pumps at a gallon a minute or can't go below 1 and the well yields way less, they're going to have a problem. they're going to have to turn the pump on off, and we don't really endorse turning pumps on and off to try to balance it out. We prefer that they bring a pump that is that has the functionality to operate at the capacity of the well. Thank you.
Okay. For well purging and sampling, what method is preferred if you have metals and VOCs?
Is that a soil question or a groundwater question?
They said well purging and sampling. He just said groundwater.
Oh, okay. And then repeat the question.
For well purging and sampling, what method is preferred if you have metals and VOCs?
I'm not too sure that there's one that's good for both. They could do sequential sampling of taking something like a low purge sample or a grab sample initially for the metals and then followed up with purging for volatiles. That is not unheard of.
Okay. What is the legal time limit to keep field books or information contained therein?
I'm going to have to ask that site remediation program for any legal time limits for those. I believe that that documentation has to be maintained for a certain amount of time. Crystal, do you have an answer?
Yeah, I don't know exactly what the time limit is, but it is not discussed in the field sampling manual.
Right.
To minimize vertical cross-contamination during the purging of deep well, considering the volumes required to do the volume averaging, could this be used to justify the use of low flow?
If it's a deep well, the chances are the water table is up in the casing. And as we mentioned before, one of the issues that we're concerned about when sampling these type of wells is how do you know that you're not getting casing water mixed in with your sample, whether you're sampling it via a low flow method or a volume average method. So one of the key components of your sampling plan is how are you going to deal with that casing water? And you can packer it off, you can try to pump it out. And as we mentioned before, if you take the option of basically lowering the water table down to the top of the open borehole or the top of the screen, if it's an overburden buried well, you can recalculate that volume that you need to take out to meet the 3 to 5 criteria just based on whatever the volume of the submerged screen would be. I think we would prefer that you take that approach than just trying to pump it at a lower rate to minimize how much water you're generating.
Okay, thank you. And that's all the time we have for questions today. Just a reminder, any questions that weren't answered during the training today will be answered via email in the next several weeks. Could you go to the next slide? Like I said, the questions that were answered will be answered via email. We ask that you fill out the course evaluation on SurveyMonkey. This is also dropped in the chat for you to click on. Feedback really helps us improve our training. Look out for an email from the CEC for certificate access. And slides and presentations will be posted on the CSRR training page in the next few weeks, so you can go back and look at the recording and look at the slides. I hope everyone has a great day, and thank you very much for coming.